On the 12th of July 2022, the world watched NASA unveil the first images from the James Webb Space Telescope. President Biden stood in the White House holding up an image of galaxy cluster SMACS 0723, showing thousands of galaxies stretching back to when the universe was just a fraction of its current age. The Space Telescope Science Institute in Baltimore had processed the data, revealing galaxies that formed 13.1 billion years ago. The images were stunning. Scientists celebrated. Everyone thought this was the beginning of a golden age of discovery. Within 3 weeks, something went terribly wrong. Astronomer Ivo Labbé at Swinburne University in Melbourne, Australia, was analysing data from something called the Cosmic Evolution Early Release Science Survey. He found a galaxy that shouldn't exist. The galaxy, given the designation CEARS 93316, appeared to be sitting at a distance that placed it just 250 million years after the Big Bang. But when Labbé and his team measured its mass, they got a number that made no sense: 100 billion times the mass of our Sunday. That's the size of the entire Milky Way galaxy, fully assembled before the universe was even 2% of its current age. The math didn't work. The timeline didn't fit. The universe is 13.8 billion years old. We know this with extreme precision from multiple independent measurements. Yet here was a galaxy that, based on its properties, would have required 15 or even 16 billion years to form. You can't have something older than the container it's sitting in. You can't bake a cake that's older than your oven. You can't have a galaxy that predates the Big Bang itself. At UCLA, astronomer Tommaso Tre was leading a different survey called GLASS, the Grism Lens Amplified Survey from Space. His team found another impossible object. Galaxy GLASS Z13 sat at a distance corresponding to just 330 million years after the Big Bang. The light from this galaxy had been travelling for 13.5 billion years before it hit James Webb's mirrors. But the galaxy itself contained stars that, according to the analysis, were already ancient when they emitted that light. The stars showed spectral signatures, specific patterns of light that only appear in stars that have been burning for hundreds of millions of years. Rohan Naidu at MIT's Kavli Institute ran the numbers on 2 more galaxies from the GLASS survey. Using spectroscopy, a technique that splits light into its component colours like a prism, his team confirmed these galaxies were truly at these extreme distances. The spectra showed something called Lyman alpha breaks and oxygen emission lines shifted so far into the infrared that Hubble could never have seen them. These weren't faint baby galaxies slowly pulling themselves together. These were massive, mature systems with organised structures, established stellar populations, and all the hallmarks of galaxies that had been evolving for a very long time. James Webb uses a primary mirror that's 6.5 meters across, about the size of a 2-story house made of 18 hexagonal segments of beryllium coated in gold. It observes in infrared light, which lets it see through cosmic dust and detect the most distant objects in the universe. The telescope sits at a point in space called L2, about 1.5 million kilometers from Earth, where it orbits in sync with our planet, while a tennis court-sized sunshield keeps it cold enough to detect the faint infrared glow from these ancient galaxies. The near-infrared camera, NIRCam, captured images of a galaxy candidate called HD1. This object appeared to be 330 million years after the Big Bang. Its brightness suggested it was either forming stars at a rate of 100 solar masses per year, meaning it was creating the equivalent of 100 suns every single year, or it contained a supermassive black hole with 100 million solar masses. Either scenario created an immediate problem. Stars that massive take time to form. black holes that massive take even longer. There simply wasn't enough time in the early universe for either to exist. Gabriel Brammer at the Niels Bohr Institute in Copenhagen took 6 of these massive galaxy candidates and calculated how old their stars actually were. He used a technique called spectral energy distribution fitting, which basically means he looked at how bright each galaxy was in different colors of light and compared that to computer models of what stars of different ages should look like. The answer he got was disturbing. These galaxies contained stars that were already 200 to 300 million years old when James Webb observed them. Here's where it gets impossible. If the galaxies were observed at 300 million years after the Big Bang, and their stars were already 300 million years old, then those stars would have formed at time zero. Actually, before time zero. The stars would have to have started forming before the Big Bang happened. That's not just unlikely or hard to explain, that's a logical impossibility. It's like finding a 50-year-old tree on an island that formed 40 years ago. The spectroscopic data showed clear signatures of what kind of stars these galaxies contained. There were indicators of what astronomers call A-type stars, stars with surface temperatures around 8,000 Kelvin, about 1.5 times hotter than the Sunday. These stars don't last forever. They burn through their fuel and evolve into giant stars over the course of about 500 million to 1 billion years. Finding these evolved stars in galaxies observed just 200 to 400 million years after the Big Bang meant that stellar evolution, the entire life cycle of stars, had somehow happened faster than physics says it can. JWST's mid-infrared instrument, MIRI, detected something else troubling: dust. Dust in space is made from heavy elements, carbon, silicon, oxygen, iron, that get cooked up inside stars and then blown out into space when those stars explode as supernovae. The presence of dust this early in cosmic history meant that multiple generations of stars had already lived and died. Each stellar generation takes tens to hundreds of millions of years. Finding third or fourth generation stars in the first 300 million years of cosmic history was like finding great-grandchildren at a birthday party for a toddler. The Hubble Space Telescope had previously held the record for the most distant galaxy ever confirmed, GNZ 11. Sitting at 400 million years after the Big Bang. That galaxy appeared as a small, faint, young-looking object, exactly what you'd expect for an early galaxy. It fit all the predictions. But James Webb was finding galaxies at even greater distances that were bigger, brighter, and more massive than GNZ 11. Instead of galaxies getting smaller and younger as you look farther back in time, they were getting larger and more mature. The universe was running backwards. Peter van Dokkum at Yale University measured one galaxy candidate, CEES 1670, and found it contained 200 billion solar masses worth of stars. That's twice the mass of the entire Milky Way, assembled in just 300 million years. The standard model of galaxy formation says that galaxies grow gradually through billions of years of mergers and gas accretion. You start with small dwarf galaxies, containing maybe 1 million stars, and over cosmic time they slowly combine and grow into larger galaxies. Finding a galaxy as massive as the Milky Way, fully formed just 300 million years after the Big Bang, was like finding a fully grown oak tree in a forest that was planted last year. The lambda cold dark matter model, the standard model of cosmology that has successfully explained virtually every observation we've made about the universe for the past 30 years, predicted very specific things about early galaxies. It said the first galaxies should be small, containing at most a few million to maybe 10 million solar masses, forming around 100 to 200 million years after the Big Bang. These baby galaxies would slowly merge over billions of years. By 500 million years after the Big Bang, you might have galaxies with 1 billion solar masses. That was the prediction. James Webb found galaxies with 10 to 100 times more mass than predicted, existing 100 to 200 million years earlier than the model said they should. It's not a small discrepancy. It's not something you can fix with a minor adjustment. This is a fundamental breakdown of our understanding. The cosmic timeline has been established with incredible precision. The Planck satellite, which mapped the cosmic microwave background radiation from 2009 to 2013, pinned down the age of the universe to 13.797 billion years, with an uncertainty of only 23 million years. That's 0.2% precision. The Wilkinson Microwave Anisotropy Probe had measured 13.772 billion years a few years earlier. Multiple other methods measuring the ages of the oldest stars, radioactive dating of meteorites, tracking the expansion rate of the universe, all converge on the same answer. The universe is 13.8 billion years old, give or take. When astronomers measure a galaxy's redshift, the amount its light has been stretched by the expansion of the universe, they can calculate how long ago that light was emitted. A redshift of 16, which several of these galaxy candidates show, means the light left that galaxy 13.55 billion years ago. The galaxy existed just 250 million years after the Big Bang. But here's the critical issue. That's the look-back time. The time the light spent travelling to us. The galaxy's own age, how long it took to form all those stars, has to be added on top of that look-back time. If the stars in a galaxy are 500 million years old, they started forming 500 million years before we see them. Add that to the 13.55 billion year look-back time, and you get stars that started forming 14.05 billion years ago. That's 250 million years before the Big Bang. The universe literally wasn't old enough yet. Time itself hadn't existed long enough for these objects to form. The moment seeing stops matching measurement a cosmic warning. The Planck satellite launched on the 14th of May 2009 from French Guiana, carried into space by an Ariane 5 rocket. For 4 years, it sat at the same L2 point where James Webb now resides, mapping every square degree of the sky in 9 different frequency bands. Its job was to measure the cosmic microwave background, the afterglow of the Big Bang itself, with unprecedented precision. Between 2009 and 2013, Planck measured the temperature of this ancient light at every point in the sky. The final data release came in 2018, and it gave cosmologists the most precise set of parameters describing our universe that we'd ever had. Planck measured the temperature of the cosmic microwave background as 2.7255 Kelvin, about minus 270 degrees Celsius, just barely above absolute zero. But it's not perfectly uniform. There are tiny variations, hot spots and cold spots, that differ by about 18 millionths of a degree. These tiny temperature differences are incredibly important because they tell us about density variations in the early universe when it was only 380,000 years old. Denser regions were slightly hotter, less dense regions were slightly cooler. These density variations eventually collapsed under gravity to form all the galaxies we see today. By analysing the pattern of these temperature fluctuations, specifically something called the angular power spectrum, which measures how the temperature varies at different angular scales across the sky, cosmologists can extract fundamental information about the universe. They can measure what fraction of the universe is made of ordinary matter, dark matter, and dark energy. They can measure how fast the universe is expanding. They can measure its geometry, and they can measure its age. The Planck team measured what's called the Hubble constant, at 67.4 kilometers per second per megaparsec. That's the rate at which the universe is expanding for every megaparsec of distance, about 3.26 million light-years. Space is stretching at 67.4 kilometers per second. They measured that ordinary matter makes up 4.9% of the universe's total energy. Dark matter accounts for 26.8%. Dark energy, the mysterious force causing the universe's expansion to accelerate, makes up 68.3%. These aren't loose estimates, they're measured to better than 1% precision. The age of 13.79, 7 billion years, isn't directly measured, it's calculated from these other parameters, using Einstein's equations for how space-time expands. The expansion rate, the matter density, and the dark energy density are all interconnected through relativity. Change one, and you have to change the others to stay consistent with observations. The age falls out of the mathematics when you run the clock backwards from the present to the moment when the universe was infinitesimally small. But now, James Webb was throwing a wrench into this beautifully precise machinery. The near-infrared spectrograph, NIRSpec, obtained spectroscopic confirmations for several galaxies at these extreme distances. The team used 28 hours of integration time, meaning they pointed the telescope at the same spot for 28 hours, collecting every possible photon using something called the microshutter array. This device has 62,000 tiny shutters, each one smaller than the width of a human hair, that open and close to isolate light from specific galaxies while blocking everything else. The spectra showed emission lines from oxygen atoms that had lost 2 of their electrons, what astronomers call doubly ionized oxygen. In a laboratory, this oxygen emission comes out at a wavelength of 5,007 angstroms in the green part of the visible spectrum. But in these distant galaxies, the emission was detected at 6.8 micrometers in the infrared, shifted by a factor of 13.6. That shift directly measures the redshift, and the redshift directly measures the distance. There's no ambiguity, no uncertainty. These galaxies are genuinely at these enormous distances. But the spectra revealed more than just distance. They showed what the galaxies were made of. The smooth background light, called the continuum, showed patterns that only appear in galaxies with mature stars. There were breaks and steps in the spectrum, sudden drops in brightness at specific wavelengths that indicate populations of older stars. The strength of certain absorption features meant these galaxies contained metals, astronomers speak for any element heavier than helium, at about 40% of what we find in the Sunday. Let that sink in. The Sun formed 4.6 billion years ago from gas that had been enriched by 9 billion years of previous stellar generations churning out heavier elements. It took 9 billion years of cosmic history to reach the Sun's metallicity. James Webb is finding galaxies with 40% of that metallicity just 300 million years after the Big Bang. The universe somehow compressed 9 billion years of chemical evolution into 300 million years. The Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, CANDLES, was a massive Hubble program that ran from 2010 to 2013. It established how many galaxies of different masses existed at different times in cosmic history. At a redshift of 8, about 600 million years after the Big Bang, Hubble found roughly one galaxy with more than 10 billion solar masses in every cubic gigaparsec of space. When you extrapolate those numbers forward to redshift 10, the prediction was clear. There should be 0 galaxies above 10 billion solar masses. Not a few, not rare ones, 0. James Webb found 87 galaxy candidates with masses above 10 billion solar masses between redshift 10 and 13. The number density wasn't 0, it was 10 to 100 times higher than Hubble predicted. Either galaxy formation was dramatically more efficient in the early universe than every simulation and theoretical model suggested, or something was fundamentally wrong with how we measure distances, ages, or masses. Or, most troubling of all, the entire cosmological framework was incorrect. The method astronomers use to estimate galaxy masses is called spectral energy distribution fitting. It's a comparison game. You measure how bright a galaxy is through multiple filters: red light, orange light, yellow, green, blue, ultraviolet. And you compare those brightnesses to computer models of what stellar populations of different ages should look like. A galaxy full of young, hot, blue stars appears bright in ultraviolet and blue light. A galaxy full of old, cool red stars appears bright in red and infrared light. By measuring the brightness in 8 to 12 different filters spanning the spectrum, you can figure out what mix of stellar ages must be present, and from that you can calculate the total stellar mass. James Webb has filters at specific wavelengths: F90W at 0.9 micrometers, F115W at 1.15 micrometers, F150W at 1.5 micrometers, F200W at 2 micrometers, F277W at 2.77 micrometers, F356W at 3.56 micrometers, F410M at 4.1 micrometers, and F444W at 4.44 micrometers. The photometric measurements through these filters showed that these early galaxies had red colors. They were bright at long wavelengths and dim at short wavelengths. That color signature indicates old stellar populations. The best fit models required stellar ages of 300 to 500 million years to match the observed colors. Cosmic reionization is the process that made the universe transparent. For the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas that absorbed ultraviolet light. Then the first stars and galaxies turned on, flooding space with ultraviolet radiation that ionized all that hydrogen, transforming it from neutral atoms into separated protons and electrons. Once ionized, the gas became transparent to UV light. This phase transition happened between roughly 300 and 1,000 million years after the Big Bang. Planck's measurements indicated that reionization was about 50% complete at 700 million years after the Big Bang. But James Webb's discovery of abundant bright galaxies at 250 to 400 million years after the Big Bang means there were far more ultraviolet emitting sources in the early universe than anyone expected. If reionization actually started at 250 million years after the Big Bang, much earlier than Planck's data indicated, then there's a tension between what the cosmic microwave background tells us and what direct observations of galaxies are showing us. One of them has to be wrong. There was hope that many of these galaxy candidates might be imposters. Without spectroscopy, astronomers estimate redshifts from colors using something called the Lyman break technique. Neutral hydrogen in space absorbs all photons with wavelengths shorter than 121.6 nanometers, the Lyman alpha lines. As you look at more distant galaxies, this absorption feature shifts to longer wavelengths. A galaxy at redshift 10 will show zero flux in blue filters and full flux in red filters, with a sharp break at a specific filter corresponding to where the Lyman alpha absorption has shifted to. The problem is that dusty galaxies at much closer distances can fake this signature. A galaxy at redshift 2, about 10 billion years ago, that contains a lot of dust might absorb its own blue light, creating an artificial break that mimics a high redshift galaxy. The only way to know for sure is spectroscopy, splitting the light and looking for specific emission lines at known wavelengths. Some candidates failed this test. Galaxy CERS 93316, initially reported at redshift 16.7 based on photometry, underwent spectroscopic follow-up in October 2022. The spectrum showed it was actually at redshift 4.9, still a distant galaxy at 12 billion years ago, but nowhere near as extreme as initially thought. This confirmation that some candidates were false positives led many astronomers to suspect that most of the high redshift candidates would turn out to be lower redshift imposters once they got spectroscopy. But other candidates passed with flying colours. JADESGSZ130, observed by the JWST Advanced Deep Extragalactic Survey, showed crystal clear emission lines confirming redshift 13.2. JADESGSZ110, confirmed at redshift 11. JADESGSZ100, confirmed at 10.38. These spectroscopic confirmations proved that at least some of the extreme candidates were real. And these real confirmed galaxies still showed masses, sizes, and metallicities that shouldn't exist at such early times. There's another crisis brewing that makes all of this worse: the Hubble tension. When you measure the expansion rate of the universe using the cosmic microwave background, you get 67.4 kilometers per second per megaparsec. But when Adam Rees at Johns Hopkins University measures it using nearby supernova explosions, a completely different method, he gets 73.2 kilometers per second per megaparsec. That's a 9% difference, and it's way larger than the measurement uncertainties. Both measurements can't be right. If the true expansion rate is 73 instead of 67, the universe is expanding faster than we thought. That means less time has elapsed since the Big Bang for the universe to reach its current size. Recalculating the age with the higher expansion rate gives you 12.8 billion years instead of 13.8 billion years. That's a billion years less time for these galaxies to form. It would make the crisis even worse. The day 250 million years ago stopped meaning what we think. Understanding what a redshift of 16 actually means requires understanding how we measure cosmic distances and times. When a galaxy is moving away from us, or more accurately, when the space between us and the galaxy is expanding, the wavelengths of light from that galaxy get stretched. Red light has longer wavelengths than blue light, so this stretching is called redshift. The amount of stretching tells us how much the universe has expanded since the light left the galaxy. The redshift factor Z is defined by comparing wavelengths. Z equals the observed wavelength minus the emitted wavelength divided by the emitted wavelength. If you observe a hydrogen emission line at 1,338 nanometers, that should be at 121.6 nanometers. The wavelength has increased by a factor of 11, giving you a redshift of Z equals 10. At redshift 16, wavelengths are stretched by a factor of 17. That 121.6 nanometer hydrogen line appears at 2067 nanometers. The relationship between redshift and cosmic time isn't straightforward. At low redshifts, it's approximately linear twice. The redshift means roughly twice the distance and twice the look-back time. But at high redshifts, the non-linear expansion history matters. The universe expanded differently when it was matter-dominated than when it became dark energy-dominated about 6 billion years ago. Converting a redshift into an age requires integrating through all these different expansion phases using the measured cosmological parameters. At redshift 1, we're seeing the universe when it was 5.9 billion years old, about 43% of its current age. At redshift 2, the universe was 3.3 billion years old, or 24% of its current age. Jump to redshift 6, and the universe was only 950 million years old, less than 7% of its current age. The relationship accelerates dramatically at higher redshifts. At redshift 10, the universe was 480 million years old. At redshift 13, just 330 million years old. At redshift 16, we're seeing the universe at 250 million years old, just 1.8% of its current age. The James Webb Primary Imager observed galaxy cluster SMACS J 723, 3 to 7,327 on the 3rd of June 2022, staring at it for 12.5 hours straight. The resulting image revealed about 46,000 galaxies scattered across that tiny patch of sky. Some of those galaxies are at redshifts exceeding 11. One galaxy, designated 738 NIR2, showed all the hallmarks of being at redshift 12.5 based on its colors. It appeared as a small red smudge in the long wavelength filters, but was completely invisible in short wavelength filters, exactly what you'd expect from the Lyman break technique. Measuring redshift definitively requires identifying specific spectral features, emission or absorption lines, at known wavelengths and measuring where they've shifted to. The strongest features astronomers look for include hydrogen, Lyman alpha at 121.6 nanometers, oxygen emission at 495.9 and 500.7 nanometers, hydrogen Balmer alpha at 656.3 nanometers, and what's called the 4000 angstrom break, where metals create a sudden drop in brightness. At redshift 13, these features shift dramatically. Lyman alpha moves to 1.7 micrometers, oxygen emission shifts to 7 micrometers, and hydrogen Balmer alpha shifts all the way to 9.2 micrometers. NIRS spec obtained a spectrum for galaxy JADES GSZ 130 using medium resolution grating that covered wavelengths from 1 to 1.8 micrometers. The exposure lasted 28 hours, spread across 14 separate visits, with the telescope returning to the target again and again. The resulting spectrum showed a strong emission line at 1.719 micrometers. Given that Lyman alpha should be at 121.6 nanometers, this means the redshift is 13.13. Additional weaker lines at 1.658 and 1.673 micrometers matched what you'd expect from nitrogen and carbon emission, confirming the interpretation. But when you model the stellar populations in JADES GSZ 130 to match its observed properties, you run into immediate problems. The galaxy contains about 500 million solar masses of stars. The star formation rate, measured from its ultraviolet brightness, is only 10 solar masses per year. At that rate, building up 500 million solar masses takes 50 million years. The universe at redshift 13 was 330 million years old. The stars themselves, based on fitting their ages from the spectrum, were already 200 million years old when we see them. Do the math. If the stars are 200 million years old and the universe is 330 million years old, star formation started 130 million years after the Big Bang. That's less than 1% into cosmic history. The first stars, what astronomers call population 3 stars, should have formed somewhere between redshift 20 and 30, corresponding to 100 to 180 million years after the Big Bang. These stars were completely different from modern stars. They formed from gas that contained only hydrogen and helium, the elements created in the Big Bang itself. Without heavier elements to help the gas cool and fragment, These primordial clouds stayed hot, and hot gas can't collapse into small chunks. The result? Population 3 stars were monsters, with masses anywhere from 50 to 500 times the Sun's mass. These massive stars burned incredibly hot and died incredibly fast. A 100 solar mass population 3 star lives for only 2 to 3 million years before it explodes. When it explodes in what's called a pair instability supernova, it completely disintegrates, no remnant left behind, and ejects 30 to 50 solar masses of oxygen, carbon, and heavier elements into the surrounding gas. This enriched gas can then form the second generation of stars, population 2 stars, which have tiny amounts of metals but enough to change their properties dramatically. The second generation can include a wider range of stellar masses, from small stars that live for trillions of years to massive ones that live for millions. The Sun is a population 1 star third generation or later formed 4.6 billion years ago from gas that had been enriched by billions of years of previous stellar generations. JADES GSZ130 shows metallicity at about 20% of the Sun's level. That means at least 2 generations of stars had to have lived and died before the stars we're observing even formed. If the first generation lived 3 million years and the second generation lived 10 million years, that's 13 million years of stellar evolution before the observed stars formed. The observed stars are 200 million years old, so they started forming 200 million years before we see them. Add it up. 13 million plus 200 million equals 213 million years of required cosmic history. But the universe at the time of observation was only 330 million years old. That leaves just 117 million years after the Big Bang for all of this to happen. It's possible, barely, but it requires everything to proceed at maximum speed, with no delays, no setbacks, no downtime. The timeline gets even more compressed when you account for dark matter halos. In the standard model, galaxies don't form in isolation. They form inside concentrations of dark matter called halos. These halos collapse under their own gravity and pull in ordinary matter. A halo massive enough to host the observed galaxy, about 100 billion solar masses of dark matter, requires roughly 100 to 200 million years to assemble through the gradual accumulation and merging of smaller halos. That process uses up most of the available time between the Big Bang and the galaxy observation, leaving almost no time for the actual stars to form and evolve. Cosmological simulations tracked this process on massive supercomputers. The illustrious simulation, run at MIT and Harvard, followed 12 billion resolution elements representing dark matter and gas in a cube 106.5 million light-years on a side. The simulation predicted that by redshift 10, the most massive halos should contain about 1 billion solar masses of dark matter. By redshift 8, they might grow to 10 billion solar masses. James Webb found galaxies with stellar masses of 10 billion solar masses at redshift 13, requiring dark matter halos of at least 100 billion solar masses. That's 300 to 400 million years earlier than simulations predicted such masses could exist. Galaxy Glass Z12 appeared with an infrared magnitude of 27.6, making it as bright as the Small Magellanic Cloud, a dwarf satellite galaxy of the Milky Way that contains about 7 billion solar masses of stars. The Small Magellanic Cloud formed over more than 10 billion years through a complex history of star formation and gas accretion. Finding a galaxy with similar brightness and mass at 390 million years after the Big Bang means star formation was happening 25 times more efficiently than it does in galaxies today. Star formation efficiency is a key concept, It measures what fraction of available gas actually turns into stars. In nearby galaxies, only about 1 to 3% of the gas in a molecular cloud successfully forms stars. The rest gets blown away by stellar winds, supernova explosions, and radiation pressure from massive stars. Early universe galaxies faced even stronger feedback because population 3 stars were more massive and more energetic. Theory predicted star formation efficiencies below 1% at redshift greater than 10. Yet fitting the observed galaxy masses and ages requires efficiencies of 10 to 30%, an order of magnitude higher than theory allows. The cosmic paradox of stars that appeared older than the universe. Stellar population synthesis, the art of converting observed light into physical properties like ages and masses, relies on detailed models of how stars evolve. Astronomers start with theoretical predictions of stellar evolution, how stars of different masses live and die, what temperatures and brightnesses they have at different ages, and what kind of light they emit. By combining thousands or millions of simulated stars with different masses and ages, following what's called the initial mass function, they create synthetic spectra that can be compared directly to observations. The Bruegel-Charlotte stellar population synthesis models, published in 2003, became the standard tool that almost every astronomer uses. These models track stars from 0.1 solar masses up to 100 solar masses at metallicities ranging from 1/50th of solar up to 2.5 times solar. For any given age and metallicity, the models predicted what the integrated spectrum should look like, the combined light from every star in the population. The library covered ages from 1 million years to 20 billion years. When astronomers fit JADESGSZ130's spectrum with these models, they found the best match required an age of 200 million years, with metallicity at about 20% of solar values. The fit also required some dust extinction. The galaxy contained interstellar dust that absorbed about 30% of its UV light. Dust grains form from heavy elements like carbon, oxygen, silicon, and iron that get produced in stellar cores and expelled by supernova explosions. The presence of dust meant previous generations of stars had already lived, died, and polluted the interstellar medium with their ashes. Population 3 stars formed from pristine primordial gas containing only hydrogen and helium, plus a tiny trace of lithium left over from Big Bang nucleosynthesis. These stars contained literally zero metals, nothing heavier than helium. They formed in what astronomers call mini-halos, dark matter halos, with masses between 100,000 and 1 million solar masses, at redshifts somewhere between 20 and 50, corresponding to 50 to 150 million years after the Big Bang. Models predict that these population 3 stars formed huge 50 to 500 solar masses. The reason comes down to cooling. When a gas cloud wants to collapse and form stars, it has to get rid of its thermal energy by radiating it away. With metals present, atoms can emit infrared light very efficiently, cooling the gas quickly, but hydrogen and helium are terrible at cooling. Without metals, gas clouds couldn't cool below about 1000 Kelvin, and at those temperatures you need a lot more mass to overcome thermal pressure and collapse. More mass means bigger stars. A 100 solar mass population 3 star burned hydrogen in its core through the CNO cycle, a set of fusion reactions using carbon, nitrogen, and oxygen as catalysts at core temperatures of 25 million Kelvin. The star's luminosity reached 1 million times the Sun's luminosity. It exhausted its core hydrogen in just 3 million years, then burned helium for 300,000 years, carbon for 600 years, oxygen for 6 months, and silicon for just one day before the core collapsed. The resulting pair instability supernova explosion completely shredded the star, leaving no remnant behind and ejecting 30 to 50 solar masses of freshly made oxygen, carbon, and heavier elements. If population 3 stars started forming at redshift 30, about 140 million years after the Big Bang, and these stars exploded after 3 million years, the first metal enrichment happened at 143 million years. Gas enriched to even tiny amounts of metals, as low as 1/10,000th of solar metallicity, could then form population 2 stars. A typical 1-0 solar mass population 2 star lives 20 million years. By 163 million years after the Big Bang, second-generation supernovae would further enrich the gas. This timeline provides barely enough time to reach 20% of solar metallicity by 330 million years after the Big Bang, and only if star formation proceeded continuously at maximum efficiency with no wasted time. The Balmer break in galaxy spectra acts like an age indicator. This is a sudden drop in brightness at 364.6 nanometers caused by hydrogen absorption in the atmospheres of stars. Young, hot O and B type stars with surface temperatures above 10,000 Kelvin have weak Balmer breaks. Older, cooler A and F type stars with surface temperatures between 6,000 and 9,000 Kelvin have strong Balmer breaks. The strength of the break tells you what fraction of your stellar population is old versus young. JWST NIRSPEC observations of galaxy CEERS 1019 at redshift 8.68, about 600 million years after the Big Bang, showed a Balmer break strong enough to require that 70% of the galaxy's stellar mass was in stars older than 300 million years. At the time of observation, the universe was 600 million years old, so 70% of the stars formed within the first 300 million years of cosmic history. That's during the transition from population 3 to population 2, when the universe was supposed to be just figuring out how to make normal stars efficiently. Oxygen abundance measurements provide another way to track stellar generations. The ratio of oxygen emission to hydrogen emission in a galaxy's spectrum tells you the oxygen to hydrogen ratio in the gas. In JADESGSZ130, this ratio indicated oxygen abundance at about 1/3 of solar values. Oxygen forms primarily in massive stars above 8 solar masses and gets expelled in Type II supernova explosions. The observed oxygen abundance meant that at least 30% of the massive stars that had ever formed in this galaxy had already exploded as supernovae before we observed it. Nitrogen to oxygen ratios provide even tighter constraints. Nitrogen forms primarily in intermediate mass stars between 3 and 8 solar masses through a complex process that requires carbon and oxygen to already be present. These stars evolve more slowly than massive stars, taking 30 to 300 million years to reach the phase where they start expelling nitrogen. The detection of nitrogen emission in some redshift greater than 1-0 galaxies indicated that at least 50 million years had elapsed since the initial starburst, giving intermediate mass stars enough time to contribute to chemical enrichment. The 4,000 angstrom break, named for its wavelength of 4,000 angstroms or 400 nanometers, measures the ratio of light just above this wavelength to light just below. The break strengthens with stellar age because older stellar populations contain more K and M giant stars, which have strong metal absorption lines in this region. Young stellar populations less than 100 million years old show weak breaks. Old populations more than 1 billion years old show strong breaks. JWST photometry suggested moderate strength breaks for some redshift about 1-1 galaxies, implying stellar ages of 300 to 500 million years. Galaxy GLASS Z11 showed colors consistent with a 4,000 angstrom break, strong enough to require at least 40% of its stellar mass in stars older than 500 million years. Since the universe was only 420 million years old at redshift 11, this implied star formation began incredibly early, within the first 10 to 20 million years after the Big Bang, during what astronomers call the Dark Ages, before the first stars were supposed to have formed. Either that, or there's something fundamentally wrong with how we interpret these spectral features in such extreme galaxies. Black holes that accreted beyond theoretical limits. On the 28th of February 2023, the JWST Advanced Deep Extragalactic Survey team dropped a bombshell. They'd found an active supermassive black hole at redshift 10.9. The galaxy hosting this black hole, with the cumbersome designation JADAS GS plus 53.18343 to 27.79097, showed emission lines that were extraordinarily broad. When astronomers see broad emission lines, lines that span thousands of kilometers per second in velocity, it means gas is orbiting something incredibly massive at incredibly high speeds. The hydrogen-Balmer alpha line in this galaxy was smeared out over 2,400 kilometers per second. The oxygen emission line was smeared over 1,800 kilometers per second. These velocities indicate gas swirling around a central black hole. Using a technique called the virial method, which assumes the gas is in gravitationally bound orbits, the team calculated a black hole mass of 40 million solar masses. That's 40 million times the mass of our Sun, concentrated into a region smaller than our solar system. The universe at redshift 10.9 was only 420 million years old. To understand how outrageous a 40 million solar mass black hole is at that time, you need to understand how black holes grow. Black holes grow by accreting material, swallowing gas and stars that get too close. But there's a speed limit to this process, called the Eddington limit. When a black hole accretes material, that material heats up and emits radiation. If the black hole tries to eat too fast, the outward pressure from all that radiation pushes away the infalling material, choking off the food supply. For a black hole with a given mass, there's a maximum rate at which it can grow, the Eddington rate. A black hole growing at the Eddington limit continuously would increase its mass by a factor of about 2.7 every 45 million years. That sounds fast, but let's run the numbers. Start with a stellar mass black hole seed, say 10 solar masses, formed from the death of one of the first massive stars. Growing at the Eddington limit for the entire 420 million years available would let it reach about 49,000 solar masses. That's nowhere close to the observed 40 million solar masses. You're short by a factor of 800. Even if you start with a more massive seed, say a 100 solar mass intermediate mass black hole from the collapse of a population 3 star growing for 420 million years at the Eddington limit, gets you 49,000 solar masses. Still way too small. To reach 40 million solar masses in the available time, you'd need to accrete at 800 times the Eddington limit continuously for hundreds of millions of years. That's not just unlikely, it's physically implausible given what we know about how accretion disks and radiation pressure work. This isn't an isolated case. JWST discovered 6 additional supermassive black holes with masses exceeding 10 million solar masses at redshifts between 8 and 11. Galaxy CEE-AIRS 1019 at redshift 8.68 hosted a 9 million solar mass black hole. Galaxy GHZ2, also called GLASS Z12, at redshift 12.1 showed X-ray emission consistent with a 1/5 million solar mass black hole. These discoveries indicated that supermassive black hole formation wasn't a rare fluke, it was common in the early universe. One way out of this timing problem involves starting with much more massive seeds. Instead of forming from individual stars, maybe some black holes formed directly from massive clouds of gas that collapsed without ever making stars. These are called direct collapse black holes. Under very specific conditions, gas staying hot enough to prevent fragmentation, intense ultraviolet radiation breaking up molecules, extremely low metallicity, a cloud could collapse directly into a black hole with a mass between 10,000 and 1,000,000 solar masses. Simulations by John Wise and colleagues found that direct collapse conditions occurred in about 1 out of every 10,000 dark matter halos at redshifts between 15 and 20. The resulting black holes, with masses between 10,000 and 100,000 solar masses, could grow to 10 million solar masses by redshift 11 through normal Eddington limited accretion. Starting from 50,000 solar masses and growing for 260 million years at the Eddington limit gets you to about 12 million solar masses. That works mathematically, but there's a catch. The conditions for direct collapse were incredibly rare, occurring in only 0.01% of halos. Yet the observed number density of supermassive black holes at redshift around 10 exceeds the predictions from direct collapse models by factors of 10 to 100. Either the conditions for direct collapse were far more common than simulations suggest, or there's another formation mechanism we haven't figured out yet. Another possibility involves primordial black holes that formed in the early universe from density fluctuations during or immediately after inflation. If quantum fluctuations during inflation occasionally produced extreme overdensities, those overdensities could collapse into black holes when they re-entered the horizon. Depending on exactly when they formed, these primordial black holes could have masses anywhere from microscopic to 100,000 solar masses. If primordial black holes with masses between 10,000 and 100,000 solar masses made up even 1% of dark matter, there would be about 1 million of them per cubic gigaparsec at redshift 20. These black holes would sink to the centers of dark matter halos and start accreting gas. By redshift 10, they could grow to 10 million solar masses, matching observations. The advantage of this scenario is that the seeds existed from the very beginning, no formation time required. But primordial black holes face tight observational constraints from gravitational microlensing, cosmic microwave background distortions, and gravitational wave observations. The X-ray emission from accreting black holes provides another constraint. When black holes swallow material, they convert 10 to 40% of that material's mass into energy, mostly in the form of X-rays. The cosmic X-ray background, the diffuse glow of X-rays coming from all directions in the sky, has been precisely measured by missions like Chandra and NuSTAR. Models predict that accreting black holes throughout cosmic history should produce a specific X-ray background intensity. If the black holes JWST found at redshift greater than 10 were accreting at the rates needed to explain their growth, their integrated contribution to the X-ray background would exceed observations by a factor of 2 to 3. The ratio of black hole mass to stellar mass creates yet another puzzle. In the local universe today, supermassive black holes contain about 0.1 to 0.2% of their host galaxy's stellar mass. Sagittarius A star, the Milky Way's central black hole, has a mass of 4 million solar masses, while the Milky Way contains about 60 billion solar masses of stars, a ratio of 0.007%. M87's black hole weighs 6.5 billion solar masses, while M87 contains 2.4 trillion solar masses of stars, a ratio of 0.27%. Jade's GS plus 53.18343 to 27.79097 has a black hole mass of 40 million solar masses and a stellar mass of 500 million solar masses. That's a ratio of 8%, about 40 to 100 times higher than galaxies today. If black holes and galaxies co-evolved over cosmic time, growing together through some connected process, why would the ratio be so dramatically different at early times? Either black holes formed first and galaxies grew around them, a top-down scenario that inverts the standard picture, or black holes somehow grew faster than stellar masses at early times, then slowed down relative to stellar growth later. The top-down scenario suggests that supermassive black holes formed independently of galaxies, perhaps from direct collapse or primordial black holes, and then attracted gas and dark matter to form surrounding galaxies. Observable consequences would include naked quasars with minimal host galaxy emission, higher black hole to stellar mass ratios at high redshift, and weaker correlations between black hole properties and galaxy properties in the early universe. Some of these predictions match what JWST is seeing. The fast growth scenario suggests normal galaxy formation, but with dramatically enhanced black hole accretion in the early universe. Higher gas densities, cold gas streams feeding material directly to galactic centers, and less efficient supernova feedback could all favor black hole growth over star formation at redshift greater than 10. As the universe evolved and gas densities declined, the balance would gradually shift toward star formation, reducing the black hole to stellar mass ratio to the values we see today. Neither scenario fully satisfies. Top-down formation requires seed mechanisms that produce massive black holes in a large fraction of halos possible, but requiring very specific conditions. Fast growth requires sustained super-Eddington accretion for hundreds of millions of years possible, but requiring special circumstances. Both scenarios need conditions in the early universe that differ significantly from theoretical expectations, pointing to missing physics in our models of the first billion years. The metals that appeared before they were cooked, the impossible elements that existed before stars forged them. On the 17th of January 2023, the European Southern Observatory announced that JWST's NIRSpec had detected carbon and oxygen emission in galaxy JADES GS Z120 at redshift 12, just 370 million years after the Big Bang. The detection came from emission lines, doubly ionized carbon at an observed wavelength of 2.49 micrometers and doubly ionized oxygen at 6.51 micrometers. The ratio of these two lines revealed something surprising about the galaxy's chemical composition. It had 8 times more oxygen than carbon, relative to what we find in the Sun. In the Sun, the oxygen to carbon ratio is about 2 to 1. This galaxy showed 16 to 1. That might not sound important until you understand where these elements come from and how long it takes to make them. Carbon forms through a process called triple alpha fusion in stars that are burning helium in their cores. 3 helium, 4 nuclei have to come together to form carbon-1,2. This requires core temperatures above 100 million Kelvin and happens in stars during specific evolutionary phases. For lower mass stars, like those between 2 and 8 solar masses, carbon production becomes efficient during the asymptotic giant branch phase. These are late-stage stars that undergo thermal pulses, dredging up carbon-rich material from their cores to their surfaces where stellar winds blow it into space. The problem is timing. A 2 solar mass star takes 800 million years to reach the carbon-producing phase. A 4 solar mass star needs 150 million years. An 8 solar mass star requires at least 30 million years. The galaxy was observed at 370 million years after the Big Bang. For 8 solar mass stars to have completed their evolution and contributed carbon, star formation must have started no later than 340 million years after the Big Bang. That's cutting it extremely close. And you'd need a lot of these stars to produce observable amounts of carbon. Oxygen forms differently. It's produced in massive stars above about 10 solar masses through the fusion of carbon and helium during core carbon-burning phases. A 1.5 solar mass star burns carbon in its core for only 600 years at temperatures around 800 million Kelvin, creating oxygen 1.6. When the star's iron core eventually collapses and explodes as a Type II supernova, all that oxygen gets blown into space. The entire process, from star formation to supernova, takes about 11 million years for a 1.5 solar mass star. The high oxygen to carbon ratio in JADESGSZ120 meant that massive stars had already lived fast and died young, exploding and enriching the gas with oxygen, while the intermediate mass stars that produce carbon hadn't yet finished their much longer evolutionary journeys. This tells us that star formation had been proceeding for at least 10 to 20 million years, long enough for massive stars to explode, but not long enough for substantial carbon production from intermediate mass stars. Nitrogen presented an even stranger pattern. JWST detected nitrogen emission in galaxy CEERS 1670 at redshift 14.3, just 250 million years after the Big Bang. Nitrogen 1.4 forms primarily through what's called the CNO cycle in intermediate mass stars. The process requires carbon and oxygen to already be present. You can't make secondary nitrogen without first having these other elements available. Nitrogen is called a secondary element for this reason. The galaxy showed nitrogen abundance at about 40% of solar values, but oxygen was only at 20% of solar values. The nitrogen to oxygen ratio was twice what we see in the Sunday. In the local universe, the nitrogen to oxygen ratio stays roughly constant at about 1 nitrogen atom for every 10 oxygen atoms across a wide range of metallicities. It only starts increasing at high metallicities when secondary nitrogen production kicks in fully. Finding high nitrogen to oxygen ratios at low metallicity at just 250 million years after the Big Bang contradicts standard nucleosynthesis predictions. Secondary nitrogen requires time to build up carbon and oxygen first, then additional time for CNO processing in intermediate mass stars. The timeline doesn't work. Either the stellar initial mass function, the distribution of stellar masses at birth, was radically different in early galaxies, heavily weighted toward intermediate masses, or nitrogen formed through primary production mechanisms in massive stars that standard models don't predict. Iron abundance added to the puzzle. Galaxy Glass Z11 showed iron emission lines in its near-infrared spectrum. Iron abundance measured at 5% of solar values, 1/20th of what the Sun contains. Even this low abundance was surprising at 420 million years after the Big Bang. Iron forms primarily through type Ia supernovae, which are thermonuclear explosions of white dwarf stars in binary systems. Type Ia supernovae occur on delay timescales. A white dwarf has to form from an intermediate mass star, which takes 30 million to 500 million years, depending on the progenitor mass. Then the white dwarf has to accrete enough material from a companion star to reach 1.4 solar masses and explode. This accretion process can take anywhere from 100 million years to several billion years. Finding any iron at 420 million years after the Big Bang means the whole process happened remarkably quickly. Core collapse supernovae from massive stars and pair instability supernovae from population 3 stars also produce iron, but in different ratios relative to oxygen. Pair instability supernovae produce iron to oxygen ratios of about 0.1, lower than the solar ratio of 0.05. Core collapse supernovae produce ratios between 0.05 and 0.1. The observed iron abundance of 5% solar at oxygen abundance 20% solar gave an iron to oxygen ratio of 0.25, 5 times higher than expected. This excess iron problem suggested either preferential iron production through some unknown mechanism or preferential oxygen loss through some process that removed oxygen but left iron behind. Dust extinction measurements complicated the picture. Interstellar dust absorbs ultraviolet and optical light, then re-emits it as infrared thermal radiation. The amount of absorption depends on how much dust is present and what the dust grains are made of. The extinction curve, extinction, as a function of wavelength, varies with dust composition. Standard curves developed for nearby galaxies might not apply to early galaxies with different chemical compositions. JWST's MIRI instrument detected thermal dust emission at 7.7 and 15 micrometers in several redshift greater than 10 galaxies. Fitting blackbody curves to this emission indicated dust temperatures between 40 and 60 Kelvin, consistent with dust being heated by young stars. The inferred dust masses ranged from 1 million to 100 million solar masses. Dust forms from heavy elements in supernova ejecta and stellar winds, with typical dust to gas mass ratios around 1%. A dust mass of 10 million solar masses implied a total gas mass of 1 billion solar masses and required 10 to 100 supernovae worth of dust production. Each supernova produces somewhere between 0.1 and 1 solar mass of dust. To accumulate 10 million solar masses of dust, you need 10 million to 100 million supernovae. If the supernova rate was 1 per year, typical for a galaxy forming stars at 10 solar masses per year, accumulating 10 million supernovae would take 10 million years. Add in the stellar evolution time of 10 million years for a 1.5 solar mass star, and you get a total of 20 million years from first star formation to dust observation. Observing this at redshift 12, when the universe was 370 million years old, meant star formation began 350 million years after the Big Bang. That's barely 2.5% into cosmic history, extremely early. And this assumes continuous star formation at maximum efficiency, with every supernova producing the maximum possible dust yield. Any inefficiencies or delays would push the required start time even earlier. The deuterium abundance provided another age constraint, though JWST couldn't measure it directly. Deuterium heavy hydrogen with 1 proton and 1 neutron formed during Big Bang nucleosynthesis, with a primordial abundance of about 25 deuterium atoms per million hydrogen atoms. Deuterium burns easily in stars at temperatures above 1 million Kelvin. All stars destroy their deuterium during pre-main sequence contraction before they ever reach the main sequence. Measuring deuterium depletion in galaxy gas would reveal how much gas had been cycled through stars. Chemical abundance patterns in individual stars within these early galaxies would provide direct evidence for multiple stellar populations if we could resolve them. Spectroscopy of individual massive stars could measure surface abundances, revealing whether they formed from pristine primordial gas, first enriched gas, or multiple generation enriched gas. Unfortunately, JWST's resolution of about 0.1 arcseconds at 2 micrometers corresponds to roughly 600 light-years at redshift 10. too coarse to resolve individual stars, but sufficient to resolve massive star clusters, containing millions of stars. The presence of polycyclic aromatic hydrocarbons, or PAS, added another layer of complexity. PAS are carbon molecules containing 20 to 100 atoms arranged in fused hexagonal rings. JWST MIRI detected PAR emission features at 6.2 and 7.7 micrometers in several redshift 10 to 12 galaxies. PAHs form in the carbon-rich envelopes of asymptotic giant branch stars and in regions where intense UV radiation from massive stars breaks apart molecules. The PAR abundance, measured by the ratio of PAR emission to total infrared luminosity, indicated that 5 to 10% of the carbon in these galaxies existed in PAR molecules. This was another indicator of chemical maturity. You don't get PAHs without substantial carbon production from evolved stars, and you don't get them distributed throughout a galaxy without time for that carbon to spread and form these complex molecules. The dark matter halos that assembled impossibly fast, the cosmic structures that grew too quickly for standard models, the lambda cold dark matter model, the backbone of modern cosmology, makes very specific predictions about how structure forms in the universe. Dark matter particles, moving at speeds much slower than light, clump together under gravity into halos, with masses ranging from 1 million solar masses for the tiniest halos up to 1,000 trillion solar masses for massive galaxy clusters. The number of halos at each mass follows mathematical formulas developed in the 1970 seconds and refined ever since. At redshift 10, about 480 million years after the Big Bang, the standard model predicted roughly 1 halo per 100 million cubic megaparsecs, with a mass above 100 billion solar masses. The observable universe contains a total volume of about 125 million billion cubic megaparsecs, which works out to about 1.25 million halos, this massive across the entire observable universe. Converting to stellar mass, assuming that about 17% of the halo mass is ordinary matter, and about 10% of that ordinary matter successfully forms stars, you'd predict maybe 100,000 galaxies with stellar masses above 1 billion solar masses at redshift 10. JWST observed about 1/100th of a square degree of sky in its deep fields like JDs and glass. When you scale those observations up to the full sky, covering 41,253 square degrees, the number density of galaxies with stellar masses above 1 billion solar masses at redshift 10 to 13 exceeded predictions by factors of 5 to 10. Galaxy candidate CEERS 1670 at redshift 14.3 showed a stellar mass of 200 billion solar masses. The standard model predicted exactly 0 galaxies, with this mass at redshift 14 across the entire observable universe. 0. Not rare, not unlikely, impossible. Yet JWST found one in its first 100th of a square degree. The extended Press-Schechter formalism tracked how dark matter halos grow through mergers over cosmic time. Monte Carlo simulations followed merger trees starting from tiny density fluctuations at 380,000 years after the Big Bang and evolving forward to redshift 10. These simulations showed that the most massive halos at redshift 10 assembled through dozens of mergers of smaller progenitor halos over 300 to 400 million years. The typical assembly time for a 100 billion solar mass dark matter halo at redshift 10 came out to 300 to 400 million years, with half the mass assembled in the final 150 million years. But stellar mass assembly should lag behind halo assembly because gas has to cool down, collapse into dense clouds, and actually form stars processes that take 50 to 100 million years. Added up, 400 million years for halo assembly, plus 50 to 100 million years for stellar assembly, equals 450 to 500 million years total. The universe at redshift 10 was only 480 million years old. That leaves essentially zero time between the Big Bang and the start of halo formation. The baryon to dark matter ratio created another ironclad constraint. Observations of the cosmic microwave background, Big Bang nucleosynthesis, and galaxy dynamics all independently established that ordinary matter makes up 4.9% of the universe's total energy density, while dark matter comprises 26.8%. In galaxy halos, this ratio means that for every 100 solar masses of dark matter, only 18.3 solar masses of ordinary matter exist. If star formation efficiency is 10%, meaning 10% of the gas successfully forms stars, only 1.83 solar masses become stars per 100 solar masses of dark matter. A galaxy with an observed stellar mass of 100 billion solar masses required a dark matter halo of 5.5 trillion solar masses. At redshift 10, the standard model predicted maybe one halo in this massive per 100,000 cubic megaparsecs across the entire observable universe. JWST found dozens of galaxies with these masses, implying either star formation efficiency was 50 to 100% instead of 10%, or the baryon to dark matter ratio was much higher than measurements indicated, or dark matter halo masses were radically different from predictions. High star formation efficiency above 50% seemed physically impossible. Star formation in molecular clouds faces constant opposition from radiation pressure, stellar winds, supernova explosions, and heating by ionizing radiation. These feedback processes expel gas from star-forming regions before it can collapse into stars. In nearby galaxies, only 1 to 3% of molecular cloud mass converts to stars per freefall time. Early galaxies with more massive stars and stronger radiation fields should have had lower efficiencies, not higher. The baryon to dark matter ratio was nailed down by two completely independent measurements. Big Bang nucleosynthesis predicted the abundances of deuterium, helium-3, helium-4, and lithium-7 based on the baryon density. Observations of primordial deuterium in distant quasar absorption systems measured the baryon density to better than 1% precision. The cosmic microwave background independently measured the same baryon density from the heights of acoustic peaks in its temperature fluctuations. Both measurements agreed perfectly, confirming the baryon to dark matter ratio at 0.183 with less than 1% uncertainty. Velocity measurements provided another way to estimate dark matter halo masses. JWST near SPEC obtained spatially resolved spectroscopy for galaxy CEARS 1019 at redshift 868, measuring how gas velocities varied across the galaxy. The velocity dispersion, the random motion of gas clouds, measured 95 kilometers per second. For a galaxy in equilibrium, this velocity dispersion relates directly to the gravitational potential, which depends on the total mass including dark matter. Using the measured velocity dispersion, the predicted dark matter halo mass came out to about 8 billion solar masses, but the galaxy's observed stellar mass was 10 billion solar masses. If the halo mass was only 8 billion solar masses, and ordinary matter was 18.3% of that, about 1.5 billion solar masses, total and star formation efficiency was 10%, the stellar mass should have been 150 million solar masses. That's 67 times less than observed. Something didn't add up. The Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, CANDELS, conducted with Hubble from 2010 to 2013, established baseline galaxy number densities at various cosmic epochs. At redshift 8, about 600 million years after the Big Bang, Hubble found approximately one galaxy with stellar mass above 10 billion solar masses per 30 cubic megaparsecs. Extrapolating this to redshift 10 using standard models predicted essentially zero galaxies with masses above 10 billion solar masses should exist. JWST found 87 galaxy candidates with stellar masses exceeding 10 billion solar masses between redshift 10 and 13. The number density exceeded predictions by factors of 100 to 1000. Either dark matter halos were far more abundant than models predicted, or galaxies formed much more efficiently inside those halos, or both. The discrepancy was too large to explain with minor adjustments. This pointed to fundamental problems with either the dark matter model or our understanding of how baryons behave in the early universe. Cosmological N-body simulations provided the most detailed predictions. The Millennium simulation, run in 2005, followed 10 billion dark matter particles in a cubic volume 500 million light-years on a side. The Illustris simulation added gas dynamics, star formation, black hole growth, and feedback processes. The Illustris TNG simulation further improved resolution and physics. All three predicted similar results. By redshift 10, the most massive galaxies should contain about 1 billion solar masses of stars assembled gradually through mergers over 400 million years. JWST found galaxies with 10 to 100 times more stellar mass. When you run these simulations forward from redshift 10 to today and compare to present-day observations, another problem emerges. If all those massive galaxies at redshift 10 were real, they should merge and grow over cosmic time, producing about 10 times more massive galaxies today than we actually observe. The co-moving number density, the number of galaxies per unit volume accounting for cosmic expansion, should stay roughly constant for the most massive galaxies. But JWST found number densities 10 times higher at redshift 10 than we see at redshift 0. The star formation rates that break physics. How the early universe rushed to create light. The specific star formation rate tells you how fast a galaxy is making new stars relative to how many stars it already has. It's calculated by dividing the star formation rate by the stellar mass. If a galaxy forms 10 solar masses of stars per year and already contains 10 billion solar masses, the specific star formation rate is 1 per gigayear, meaning it would double its stellar mass in 1 billion years if it maintained that rate. Galaxies in the local universe today show specific star formation rates around 0.1 to 1 per gigayear. The Milky Way forms about 2 solar masses of stars per year and contains 60 billion solar masses, giving a specific star formation rate of 0.033 per gigayear. That means the Milky Way would take 30 billion years to double its stellar mass at the current rate longer than the age of the universe. Starburst galaxies like M82, which are undergoing intense bursts of star formation triggered by gravitational interactions with neighboring galaxies, show specific star formation rates around 10 per gigayear. Observations at redshift 2 to 3, the peak epoch of cosmic star formation about 10 to 11 billion years ago, showed typical specific star formation rates of 2 to 4 per gigayear. That was considered high. Galaxies at that era were forming stars much more actively than galaxies today. JWST observations at redshift 10 to 13 revealed specific star formation rates of 20 to 100 per gigayear. Galaxy Glass Z11 showed a star formation rate of 15 solar masses per year, measured from its ultraviolet brightness, and a stellar mass of 3 billion solar masses, giving a specific star formation rate of 50 per gigayear. At that rate, the galaxy would double its stellar mass every 20 million years. In 100 million years, it would grow by a factor of 32. Starting from a stellar mass equal to a large globular cluster, 100 million solar masses, it could reach 3.2 billion solar masses in 100 million years just by maintaining this frantic pace. The problem is that specific star formation rates can't remain constant at these extreme values for long periods. Star formation consumes gas. The gas reservoir gets depleted. Intense star formation also creates feedback. Massive stars emit powerful radiation that heats surrounding gas. Stellar winds blow gas away, and supernova explosions violently expel material from the galaxy. The feedback timescale, the time it takes for stellar energy injection to heat gas to escape velocity, runs somewhere between 1 and 10 million years. After one feedback time, star formation should decline dramatically or shut off completely until new gas can cool and fall back in. The duty cycle measures what fraction of time a galaxy spends actively forming stars versus sitting quiescent with little star formation. A duty cycle of 100% means continuous star formation. A duty cycle of 10% means short bursts of star formation lasting perhaps 1 million years, separated by 9 million years of quiescence. Observations of local starburst galaxies show duty cycles between 10 and 50%. If early galaxies had similar duty cycles, the star formation rates JWST measured represented peak rates during bursts, not time average rates. Even accounting for duty cycles, the specific star formation rates remain 5 to 10 times higher than theoretical expectations. The equilibrium-specific star formation rate, the rate that balances gas accretion, star formation, and feedback, depends on the gas fraction and the depletion time. The gas fraction is the ratio of gas mass to total baryon mass. The depletion time is how long it would take to consume all the gas at the current star formation rate. For reasonable values, say 50% of baryons in gas and a depletion time of 100 million years, the equilibrium-specific star formation rate comes out to 5 per gigayear. JWST values exceeded this by factors of 4 to 20. High gas fractions could partially explain this. If 90% of baryons remained as gas, with only 10% in stars, and the depletion time was 100 million years, you'd get a specific star formation rate of 9 per gigayear. That's closer, but still falls short of observations. Alternatively, short depletion times could boost the specific star formation rate. If gas was consumed in 10 million years instead of 100 million years, the specific star formation rate would increase by a factor of 10. Depletion time depends on gas surface density, how much gas is packed into a given area. Higher surface densities lead to faster star formation per unit area. The Kennicutt-Schmidt law, established from observations of nearby galaxies, relates star formation rate surface density to gas surface density. Higher gas density means proportionally higher star formation rate. Galaxy JADE SGS Z130 had an effective radius of 0.3 kiloparsecs, only 980 light-years across. With a stellar mass of 5 billion solar masses, the stellar mass surface density came out to 18 million solar masses per square parsec. Assuming the gas to stellar mass ratio was 2 to 1, the gas surface density would be 36 million solar masses per square parsec, 100 times higher than the Milky Way's disk. Such extreme gas densities should indeed produce rapid star formation. But there's a problem. Plugging these densities into the Kennicutt-Schmidt law predicted star formation rates of 250,000 solar masses per year, far exceeding the observed 15 solar masses per year. The discrepancy indicated either the Kennicutt-Schmidt law broke down at extreme densities, or the galaxies weren't in equilibrium, or the size measurements were wrong and galaxies were actually larger and less dense than measured. JWST imaging at 2 micrometers had a resolution of 0.063 arcseconds, corresponding to 360 light-years at redshift 13. Galaxies smaller than this appeared as unresolved point sources, making accurate size measurements impossible. Many of the early JWST galaxies appeared as barely resolved fuzzballs, only 2 to 3 pixels across. Measuring their true sizes required careful modelling of the point spread function, the blurring caused by the telescope's optics, and deconvolving that from the true galaxy structure. Gravitational lensing provided higher effective resolution. Galaxy cluster SMACS 0647 at redshift 0.59 magnified background galaxies by factors of 5 to 20, depending on their position behind the cluster. JWST observed galaxy SMACS 0647JD at redshift 10.17 behind this cluster, and found it gravitationally lensed into 3 separate images, separated by 8 arcseconds. The magnification was 8 plus or minus 2. Careful modelling of the gravitational lens allowed reconstruction of the source galaxy's true properties. The unlensed source had a size of 200 parsecs, 650 light-years, much smaller than initially estimated from the lensed images. The stellar mass was 300 million solar masses. The star formation rate was 4 solar masses per year. That gave a specific star formation rate of 13 per gigayear high, but more reasonable than estimates from unlensed galaxies. The small size meant the stellar mass surface density was 2.4 million solar masses per square parsec, and the star formation rate surface density was 32,000 solar masses per year per square kiloparsec. These values matched local starburst galaxies. This lensed galaxy suggested that at least some of the extreme properties seen in unlensed early galaxies might be artifacts of uncertain size measurements. If the true sizes were smaller than estimates suggested, the surface densities would be higher, but the total masses and star formation rates would be lower, bringing the specific star formation rates closer to theoretical expectations. However, even with these corrections, the values remained 2 to 5 times higher than models predicted. The cosmic star formation rate density, the total amount of stars forming per unit volume integrated over all galaxies, gave a volume averaged rate of 0.01 solar masses per year per cubic megaparsec at redshift 10. Extrapolating to redshift 13, the rate was roughly 0.003 solar masses per year per cubic megaparsec. Integrating this over the 250 million years from the Big Bang to redshift 13 gave a total stellar mass density of about 800,000 solar masses per cubic megaparsec. Converting to the fraction of baryons locked up in stars, the baryon density in the universe is about 5 billion solar masses per cubic megaparsec. Having 800,000 solar masses in stars means 0.01, 6% of baryons had been converted to stars by redshift 13. That sounds low and reasonable, but the devil's in the details. Forming 0.016% of baryons into stars in 250 million years required an average specific star formation rate of 0.6 per giga-year, which was consistent with expectations. The problem wasn't the total amount of stellar mass formed, it was the rate at which individual galaxies were forming it and how early they started. JWST was observing individual galaxies with specific star formation rates, 50 per gigayear, nearly 100 times the cosmic average. Either these galaxies were incredibly rare outliers caught during their brief periods of maximum activity, or the sample was heavily biased toward extreme starbursts, or the measurements were systematically overestimating star formation rates. The impossible galaxy sizes and rotation curves. When galaxies defy physics, disk galaxies form when gas with angular momentum collapses and conserves its spin. Angular momentum, the rotational analogue of linear momentum, determines disk size through a straightforward relationship. Larger angular momentum produces bigger disks. Lower angular momentum produces compact systems. Dark matter halos acquire their angular momentum through gravitational interactions during the cosmic web's formation. As matter collapses into halos, tidal torques from nearby structures spin them up. Theory predicts a dimensionless spin parameter, a number that characterizes how much rotation a halo has of about 0.03 to 0.05 for typical dark matter halos. For a halo with a mass of 100 billion solar masses and a size of 30 kiloparsecs, this spin parameter corresponds to a specific amount of angular momentum. When gas falls into this halo and collapses to form a disk, conserving that angular momentum leads to a predicted disk size of about 50 parsecs, just 160 light-years across. But observed disk galaxies today have sizes of 3 to 10 kiloparsecs, that's 10,000 to 30,000 light-years across. They're 60 to 200 times larger than the simple angular momentum conservation predicts. This discrepancy, called the angular momentum catastrophe, troubled theorists for decades. The resolution involved supernova feedback redistributing angular momentum. Gas in galactic centers with low angular momentum gets preferentially expelled by supernova explosions, while high angular momentum gas in outer regions stays put. Over multiple cycles of inflow and outflow, the average angular momentum of the remaining gas increases, producing realistically sized disks. JWST observations at redshift 10 to 13 showed rotating disk galaxies, which was surprising given how young these systems were. Galaxy JADESGSZ110 showed a clear velocity gradient across its structure. One side was blue shifted by 80 km per second, while the opposite side was redshifted by 80 km per second. This indicated rotation with a total velocity of 160 km per second. The galaxy's effective radius was 450 parsecs. For a rotating disk, the total angular momentum depends on mass times velocity times radius. With 3 billion solar masses rotating at 160 km per second at a radius of 450 parsecs, the angular momentum worked out to about 200 trillion solar masses times kiloparsec times kilometers per second. Comparing this to what you'd expect from the dark matter halo calculating the spin parameter gave a value of 0.09. That's about twice as high as theoretical predictions of 0.03 to 0.05. This elevated spin parameter meant either the halo had unusually high rotation, or the baryons retained more angular momentum than expected, or the galaxy had acquired extra angular momentum through mergers or accretion of high angular momentum gas streams. Any of these scenarios required special circumstances that shouldn't be common in the early universe. The rotation curve orbital velocity as a function of radius tests whether galaxies are rotationally supported or pressure supported. Rotationally supported systems, like spiral galaxies, show rising rotation curves in their inner regions that flatten out at large radii. Pressure-supported systems, like elliptical galaxies, show relatively flat velocity dispersion profiles. The ratio of rotation velocity to velocity dispersion, called V over sigma, quantifies this. Disks have V over sigma greater than 1, ellipticals have V over sigma less than 1. Galaxy JADESGS Z110's velocity gradient suggested rotation, but JWST's spatial resolution of 0.1 arcseconds, corresponding to 580 parsecs at redshift 11, was barely sufficient to measure any gradient at all. Getting detailed rotation curves requires resolving the galaxy into at least 5 to 10 independent resolution elements, which wasn't possible for most of these compact early galaxies. One galaxy at redshift 9.1, SMACS 416 Y1, was observed by ALMA in carbon monoxide emission, providing much better spatial resolution and a clear rotation curve measurement. Galaxy sizes followed a well-established relationship with stellar mass in the local universe. More massive galaxies tend to be larger, following a power law where size scales with stellar mass to the 0.22 power. At redshift 2, this relationship was established by hundreds of Hubble observations. Extrapolating to redshift 10 using the expected evolution sizes should be smaller at earlier times, predicted effective radii around 0.4 to 0.5 kiloparsecs for galaxies with 10 billion solar masses. JWST observations showed sizes ranging from 0.3 to 0.8 kiloparsecs. For these masses generally consistent with predictions, but with substantial scatter. Several galaxies fell significantly above the relation. Galaxy CEERS 1670 at redshift 14 with 200 billion solar masses showed an effective radius of 1.2 kiloparsecs, twice the predicted 0.6 kiloparsecs. Large sizes indicated rapid growth over large volumes, inconsistent with the gradual inside-out assembly predicted by hierarchical models where dense centers form first and outer regions accrete later. The compactness parameter, stellar mass divided by radius squared, quantified how concentrated stellar mass was. High compactness meant dense galaxies, low compactness meant diffuse galaxies. Local ellipticals had compactness around 100 million solar masses per square kiloparsec. Local spirals had compactness around 10 million solar masses per square kiloparsec. JWST redshift 1-3 galaxies showed compactness ranging from 10 million to 10 billion solar masses per square kiloparsec, spanning the full range from diffuse to ultra-compact with no clear preference. Some galaxies were ultra-compact, with compactness exceeding 1 billion solar masses per square kiloparsec. These resembled objects called red nuggets, compact quiescent galaxies, observed at redshift 2 to 3, thought to be progenitors of massive ellipticals. Red nuggets formed through gas-rich major mergers that funneled gas to galactic centers, triggering intense starbursts that assembled stellar bulges in less than 100 million years. Finding similar ultra-compact galaxies at redshift 13 suggested major mergers were already occurring within the first 300 million years earlier than theory predicted galaxy mergers should become common. Galaxy morphologies showed surprising diversity. Some appeared smooth and symmetric, like ellipticals or face-on-disk galaxies. Others showed clumpy, irregular structures suggesting either ongoing mergers or violent disk instabilities. A few showed clear spiral arm patterns. Galaxy CEERS 1062 at redshift 9.5 displayed two-armed spiral structure with well-defined pitch angle. Spiral arms form from density waves in rotating disks driven by gravitational instabilities. Their presence indicated well-organized rotation and self-gravity hallmarks of mature galaxies, not newly forming systems. Clumpy galaxies comprised about 40% of JWST's redshift 10 to 13 sample. These systems showed multiple bright star-forming regions with sizes of 50 to 200 parsecs and masses between 10 million and a billion solar masses, similar to giant molecular clouds in nearby galaxies, but brighter, more massive. These clumps might be giant star-forming complexes, or they might be separate proto-galaxies in the process of merging together. The clump survival time, how long these features persist before merging into the central galaxy, determined whether clumpy galaxies evolved into smooth ellipticals or maintained their disturbed appearance. Dynamical friction between clumps and the background disk caused them to spiral inward on timescales of 100 to 300 million years. If we are observing galaxies 50 to 100 million years after clump formation, we'd catch them in their clumpy phase before they settled down. But if these clumps persisted for their full dynamical friction timescale, galaxies should remain clumpy for substantial fractions of a billion years. The observations that could save or destroy the Big Bang, how one discovery can rewrite cosmic history. Following JWST's initial discoveries, multiple observational programs launched worldwide to either confirm or refute the controversial findings. These programs used JWST's spectroscopic capabilities, ALMA's millimeter observations, and ground-based telescopes to obtain definitive measurements of redshifts, stellar populations, dust content, and gas properties for galaxies at redshift greater than 10. JWST Cycle 2, which started in July 2023, allocated 1,200 hours specifically for follow-up spectroscopy of high redshift galaxy candidates. The JD's Origins Field Program received 300 hours for deep NIRSPEC spectroscopy, targeting 200 galaxies with photometric redshifts above 10. By October 2023, spectroscopic confirmations had been obtained for 42 galaxies, 8 at redshift 10 to 11, 3 at redshift 11 to 12, and 1 at redshift 12 to 13. The highest spectroscopically confirmed redshift as of early 2024 was 13, 2 for JADES GSZ 130. ALMA Cycle 9, observations between 2022 and 2023 targeted 25 JWST galaxy candidates at redshift 10 to 14, searching for dust continuum emission at 1.2 millimeters and carbon monoxide line emission. As of February 2024, 3 galaxies had been detected in dust continuum: SMACS 416 Y1 at redshift 8.31 with a dust mass of 50 million solar masses, GLASS Z12 with a tentative detection, and CEERS 1536 at redshift 8.6 with 30 million solar masses of dust. Carbon monoxide detections numbered 2, SMACS 416 Y1 and CEERS 1536. The remaining 22 galaxies showed no detections, constraining their dust masses below 10 million solar masses. Keck Observatory's Moss-Fire near-infrared spectrograph obtained independent spectroscopic confirmations for 5 redshift greater than 10 candidates during 2023 observing runs. Keck confirmed CEERS 93316 at redshift 4.9, dramatically lower than the initial photometric estimate of 16.7. This was a major downgrade, revealing photometric redshift uncertainties. 3 other candidates confirmed at redshift 10.1, 10.8, and 11.4, validating JWST identifications for some galaxies while revealing significant contamination for others. The contamination rate galaxies with photometric redshift above 12 that actually sat at redshift below 6 measured 20 to 40% depending on selection criteria. The Hobby Eberly Telescope Dark Energy Experiment, HETDEX, used the virus spectrograph to search for Lyman alpha emission from JWST candidates. Between August 2023 and March 2024, HETDEX observed fields containing 47 JWST candidates with photometric redshifts 10 to 12. Lyman alpha detection rate was only 8%, 4 detections out of 47 targets. This was significantly lower than the predicted 15 to 30% if candidates were truly at their claimed redshifts. The low detection rate suggested candidates were either at lower redshift, where Lyman alpha fell outside the observed wavelength range, or neutral hydrogen in the intergalactic medium absorbed Lyman alpha even at redshift less than 11, or intrinsic Lyman alpha emission was weak. Gravitational lensing programs used JWST to observe massive galaxy clusters that magnified background galaxies. The UNCOVER program spent 180 hours observing cluster SMACS 0416, detecting 32 lensed galaxies at photometric redshifts 9 to 11 with magnifications ranging from 5 to 50. Lensing enabled resolved imaging showing galaxy substructure star-forming clumps, spiral arms, irregular features impossible to detect in unlensed galaxies. One lensed galaxy at redshift 10.17 resolved into 3 clumps, each about 50 parsecs across and containing 100 million solar masses. Ground-based telescopes obtained rest-frame optical spectroscopy for redshift 7 to 9 galaxies using instruments like Keck Mossfire, VLT, KMOS, and Gemini GNIRS. These observations measured hydrogen, Balmer alpha, and nitrogen emission lines, determining accurate redshifts, metallicities, and ionization states. Results showed metallicities between 0.1 and 0.3 times solar for redshift 7 to 9 galaxies, consistent with JWST measurements for redshift 10 to 13 galaxies. This suggested chemical evolution wasn't dramatically different between redshift 7 and 13. Comparison of JWST photometry with ground-based spectroscopy revealed systematic photometric errors. For 15 galaxies with both JWST photometry and ground-based spectra, photometric redshifts overestimated spectroscopic redshifts by an average of 0.4 with a scatter of 0.8. 3 galaxies showed discrepancies greater than 2, photometric redshift 13, but spectroscopic redshift 5. These large errors highlighted the difficulty of estimating redshifts from colors alone, especially for dusty galaxies that could mimic high redshift Lyman breaks. The next few years will be critical. JWST Cycle 3 and 4 programs will obtain spectroscopy for hundreds more candidates, either confirming or refuting the most extreme claims. ALMA will search for molecular gas and dust in larger samples. The next generation of extremely large telescopes, the Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope will come online in the late 2022 with capabilities to spectroscopically confirm even the faintest early galaxies. The tension might resolve in several ways. If most extreme candidates turn out to be lower redshift interlopers, the crisis fades and standard cosmology survives with minor modifications. If spectroscopy confirms most candidates at their extreme redshifts, cosmology faces a genuine revolution requiring new physics, modified gravity, different dark matter properties, or even revised expansion history. If results fall somewhere in between, with some confirmations and some failures, theorists will need to explain why galaxy formation was more efficient than models predicted while keeping the basic cosmological framework intact. Why the standard cosmological model might be fundamentally broken. The lambda cold dark matter model rests on 6 parameters measured with extraordinary precision from the cosmic microwave background, supernovae, and large-scale structure. These 6 numbers, the Hubble constant, baryon density, cold dark matter density, dark energy density, the scalar spectral index, and optical depth to reionization, predict everything from the universe's age to when galaxies should form. These parameters are measured to about 1% accuracy, creating an incredibly tight web of predictions. If any one parameter was significantly wrong, predictions for galaxy formation, cosmic ages, and structure formation would all change in connected ways. The Hubble tension represents the most prominent crack in this framework. Early universe measurements from Planck's cosmic microwave background give 67.4 kilometers per second per megaparsec. Late universe measurements from Adam Riess's supernova program give 73.2 kilometers per second per megaparsec. That's a 9% discrepancy way beyond measurement uncertainties. If the true expansion rate is 73 instead of 67, the universe is expanding faster than Planck indicated. Faster expansion means less time has elapsed since the Big Bang for the universe to reach its current size. Recalculating with the higher expansion rate gives a universe age of 12.8 billion years instead of 13.8 billion years. That's a billion years less time for these early galaxies to form, making the crisis dramatically worse, not better. But it also suggests the Planck-based cosmological model might be wrong in fundamental ways that affect other calculations too. Alternatively, if early universe measurements are wrong, if the true Hubble constant is 67, but something about analyzing the cosmic microwave background is incorrect, then predicted galaxy formation timescales might be off. Specifically, if dark matter density was lower than measured, say 20% of critical density instead of 27%, structure formation would proceed more slowly with less gravity to collapse matter. But this would make the problem worse. Not better, slower structure formation means even less ability to form massive galaxies early. The scalar spectral index measures how the amplitude of primordial density fluctuations varied with scale. Planck measured 0.965, plus or minus 0.004, indicating slightly more power at large scales than small scales. If the true value was exactly 1, representing perfect scale invariance, small-scale power would increase by about 4%, potentially enhancing collapse of small halos at early times. But this value is ruled out at 8 sigma significance. You'd need the measurement to be wrong by 8 times its uncertainty. That's extraordinarily unlikely. Modifications to dark matter properties offer another possibility. Standard cold dark matter consists of massive particles moving slowly compared to the speed of light. Warm dark matter particles with masses around 1 kilo electron volt move faster, suppressing small-scale structure formation. Warm dark matter models successfully predict fewer dwarf galaxies today, potentially solving what's called the missing satellites problem. But warm dark matter also predicts fewer small halos at high redshift, making the tension with JWST observations worse, not better. Self-interacting dark matter, where dark matter particles scatter off each other through some new force, alters density profiles in halo centers, creating cores instead of cusps. This affects galaxy rotation, curves and sizes at redshift 0 today, but has minimal impact on halo abundance or assembly times at redshift greater than 10. Self-interacting dark matter provides no resolution to JWST tensions. Modified gravity theories that replace dark matter entirely face severe challenges. Mond-modified Newtonian dynamics successfully explains galaxy rotation curves without invoking dark matter, but struggles to explain the cosmic microwave background, large-scale structure, and gravitational lensing observations. Extensions like TVES tensor vector scalar gravity partially address these, but make no specific predictions about redshift greater than 1-0 galaxy abundances that differ substantially from standard cosmology. Early dark energy models proposed that dark energy density was higher in the early universe than today. This would accelerate cosmic expansion during structure formation, mimicking effects of lower matter density. Some early dark energy models reduce structure growth at redshift less than 3, while paradoxically enhancing growth at redshift greater than 10 through modified background expansion. Certain parameter choices predict 20 to 50% more massive halos at redshift 10 to 13, potentially explaining JWST observations while maintaining consistency with lower redshift observations. Primordial black holes comprising dark matter provide an alternative scenario. If dark matter consisted of black holes with masses between 10,000 and 1 million solar masses formed during inflation, these black holes could serve as seeds for galaxy formation. Galaxies forming around primordial black hole seeds would grow faster than galaxies forming in standard dark matter halos, requiring gradual assembly through hierarchical mergers. However, primordial black holes are constrained by gravitational microlensing, cosmic microwave background distortions, and LIGO gravitational wave observations to comprise less than 1% of dark matter insufficient to significantly alter galaxy formation. Varying fundamental constants, scenarios where physical constants, like the fine structure constant or Newton's gravitational constant, were different at high redshift, could affect structure formation and stellar evolution. A higher gravitational constant at redshift greater than 10 would strengthen gravity, accelerating halo collapse and star formation. But measurements of atomic transition frequencies in distant quasars constrain changes in the gravitational constant to less than 1 part in 100,000 over cosmic time, too small to explain JWST observations. Cyclic cosmology scenarios, where the universe undergoes repeated cycles of expansion and contraction, might allow structure from previous cycles to seed current cycle galaxy formation. If our Big Bang was actually a bounce from a previous contracting phase, density fluctuations could enter the current cycle pre-amplified, accelerating structure formation. But observational evidence for cyclic cosmology, specific signatures in the cosmic microwave background or gravitational wave backgrounds, remains absent. The most conservative resolution involves systematic errors in JWST observations or their interpretation. Photometric redshift errors, placing 50% of redshift greater than 1-3 candidates. At lower redshifts, around 5 to 8, would halve observed number densities, partially resolving tensions. Stellar mass overestimates by factors of 2 to 3 due to incorrect stellar population assumptions, top-heavy initial mass functions, or active galactic nucleus contamination would reduce required assembly times. Spectroscopic follow-up over the next few years will prove crucial in determining which galaxies are truly at extreme redshifts and which are lower redshift interlopers. The alternative explanations that might rescue everything, possible solutions to the Big Bang paradox. Rather than abandoning the Big Bang model entirely, several alternative explanations attempt to reconcile JWST observations with standard cosmology through revised assumptions about early galaxy formation, dust properties, or stellar populations. These explanations don't require inventing new physics, just applying existing physics differently to extreme early universe conditions. Dust-obscured star formation represents one possibility. If galaxies experienced intense, dust-obscured starbursts 500 million years before observation, stellar populations 500 million years old would dominate the mass budget. But dust obscuration would hide the oldest stars from view. JWST's ultraviolet and optical observations would detect only younger stars, less than 200 million years old, that haven't yet been hidden by dust, leading to age estimates biased toward youth. The true stellar populations would be much older than measurements suggest. Testing this requires mid-infrared spectroscopy, detecting polycyclic aromatic hydrocarbon features and silicate absorption at 10 micrometers, rest frame redshifted to 130 micrometers at redshift 13. This wavelength range is accessible to ALMA or future missions like the Origin Space Telescope. If silicate absorption is detected, dust-obscured older populations are present. JWST MIRI observations at 7.7 and 15 micrometers detected thermal emission but lacked spectral resolution to identify specific absorption features, leaving this possibility open. Top-heavy initial mass functions, stellar populations weighted toward massive stars rather than the standard distribution peaking at low masses, would increase luminosity per unit stellar mass. Standard stellar population models like Salpeter or Krupa predict average stellar masses around half a solar mass. A top-heavy initial mass function with the peak at 10 solar masses instead of 0.3 solar masses would increase average stellar mass to about 2 solar masses, reducing inferred stellar masses by a factor of 4 for a given luminosity. Top-heavy initial mass functions occur under conditions with low metallicity below 0.001 times solar and high temperatures above 1000 Kelvin, characteristic of population 3 star formation. If redshift 1 0 to 1, 3 galaxies formed stars with population III, like initial mass functions, stellar masses are overestimated by factors of 3 to 5. This partially explains high specific star formation rates. If true stellar mass is 1 billion solar masses instead of 3 billion, specific star formation rate drops from 50 per gigayear to 15 per gigayear, more plausible, though still high. Testing initial mass function variations requires measuring stellar mass to light ratios through dynamical methods. Comparing observed rotation velocities from spectroscopy to luminosities determines mass to light ratios. If dynamically measured masses are lower than masses inferred from luminosity assuming standard initial mass functions, the initial mass function is top-heavy. JWST observations provide luminosities. Velocity measurements from NIRSpec give rotation speeds around 100 km per second. Sizes around 0.3 kiloparsecs give dynamical masses around 3 billion solar masses, comparable to spectral energy distribution fitted stellar masses, suggesting reasonably standard initial mass functions. Active galactic nucleus contribution to ultraviolet luminosity could artificially inflate stellar mass estimates. Supermassive black holes accreting gas emit power law continua across ultraviolet optical infrared wavelengths. Adding 30% active galactic nucleus contribution to ultraviolet light increases inferred stellar mass by factors of 1.5 to 2, depending on stellar population, age, and dust content. If 20 to 40% of redshift greater than 10 galaxies contain active galactic nuclei, median stellar masses are overestimated by 30 to 50%. Identifying active galactic nuclei requires detecting broad emission lines, with velocities exceeding 1,000 kilometers per second, or high ionization lines like helium-2, nitrogen-V, or carbon IV, with equivalent widths exceeding stellar photoionization predictions. JWST NIRSPEC spectra of 37 galaxies at redshift 7 to 10 found broad lines in 3 galaxies, an 8% active galactic nucleus fraction, and strong high ionization lines in 6 galaxies, 16%, possibly containing active galactic nuclei. Total active galactic nucleus fraction around 20% would reduce average stellar masses by roughly 15%, helpful but insufficient to resolve factor of 1-0 discrepancies. Stochastic star formation random bursts, rather than continuous activity, affects age and mass measurements. If galaxies experienced 1-0 million-year bursts, forming a billion solar masses separated by 5-0 million-year quiescent periods, observed properties depend on whether we catch them during bursts or quiescence. Bursts show high star formation rates, around 100 solar masses per year, blue colors from young populations, and modest stellar masses. Quiescence shows low star formation rates below 1 solar mass per year, red colors from aging populations, and accumulated stellar masses from previous bursts. Spectral energy distribution fitting to burst phases yields ages around 10 million years and masses around 1 billion solar masses. Fitting quiescent phases yields ages around 50 million years and masses around 3 billion solar masses. Time averaging over multiple cycles gives effective ages around 30 million years and masses around 2 billion solar masses lower than fitting individual quiescent observations. If 70% of JWST galaxies are observed during quiescence and 30% during bursts, average stellar masses are overestimated by roughly 30%. Testing stochastic star formation requires repeat observations, monitoring star formation rate variability. JWST observed some fields in multiple epochs. JDES visited Good South in October 2022, January 2023, and May 2023. Comparing images detected star formation rate variations in 5% of galaxies, too few to explain systematic overestimates. But longer baselines, spanning years, might reveal more variability. Environmental effects from location in overdense or underdense regions affect galaxy properties. Galaxies in protoclusters accrete more gas, merge more frequently, and form stars faster than isolated field galaxies. If JWST preferentially observed protocluster members due to gravitational lensing amplifying protocluster fields, observed galaxies would be biased toward higher masses and star formation rates than typical field galaxies. Correcting for environmental bias requires large area surveys spanning diverse environments. JWST's first-year observations covered 0.2 square degrees concentrated in lensing clusters like MACS 0416, SMACS 0723, and Abell 2744, plus deep fields like Good South and Good North. These fields might contain 2 to 5 times overdensities, biasing samples toward extreme galaxies. Future surveys like Cosmos Webb, covering 0.5 square degrees in the Cosmos field, will sample more typical environments. Revised stellar population models incorporating binary star evolution, stellar rotation, and improved opacity calculations predict bluer colors and weaker Balmer breaks for given ages, systematically increasing age estimates by 20 to 40%. If JWST observations are fitted with older stellar libraries like Brujual Charlotte 2003 models, ages would be underestimated. Refitting with updated models like BPAS, MIST, or FSPS would increase ages. But this worsens tensions rather than resolving them. Conversely, uncertainties in stellar atmospheres at low metallicity below 0.01 times solar, our large model predictions vary by 30 to 50% in ultraviolet fluxes. If true stellar spectra differ from models, ages derived from spectral energy distribution fitting could be wrong by factors of 1.5 to 2. Validating models requires spectroscopy of extremely metal-poor stars in the Milky Way halo or globular clusters, work ongoing but not yet definitive. The luminosity function that defies all predictions. The galaxy luminosity function describes how many galaxies exist at each brightness level. It's one of the most fundamental measurements in extragalactic astronomy. The Schechter function, developed in 1976, provided a mathematical formula fitting observations across cosmic time. It has 3 parameters: a normalization setting the overall number density, a characteristic luminosity, where the function transitions from power law to exponential, and a faint end slope determining how steeply galaxy numbers increase toward fainter magnitudes. At redshift 0 today, measurements give a characteristic absolute magnitude around -20.7, corresponding to a luminosity of 14 billion solar luminosities. The faint end slope is -1.3, meaning galaxy numbers increase toward fainter magnitudes but not too steeply. The exponential cutoff at bright magnitudes means very luminous galaxies are exponentially rare. At redshift 2 to 3, during peak cosmic star formation, the characteristic magnitude brightened to -21 and the faint end slope steepened to -1.6, reflecting more vigorous star formation. JWST observations at redshift 10 to 13 measured the ultraviolet luminosity function at rest frame 1,500 angstroms, tracing emission from hot young stars. The apparent magnitude limit of NIRCam imaging was 29.5 at 5 sigma detection in 2-hour exposures. At redshift 13, accounting for distance and cosmological effects, this corresponded to an absolute magnitude of -17.8. Galaxies brighter than this were detectable. Fainter galaxies were missed. The survey volume, the comoving volume, accessible to observations depended on survey area and redshift range. JDES covered 236 square arc minutes, about 0.002% of the full sky, spanning redshift 10 to 14. The comoving volume was 2 cubic megaparsecs, with 87 galaxies detected brighter than absolute magnitude -17.8. The number density was 43 per cubic megaparsec, for bright galaxies far exceeding predictions. Fitting Schechter functions to JWST data required measurements across a wide luminosity range. JWST detected galaxies from absolute magnitude -17.8 up to -22.5 for the brightest objects, spanning 4.7 magnitudes. Fitting 3 parameters to this range was feasible, but with substantial uncertainties due to small sample sizes and cosmic variance. Best fit parameters at redshift 10 to 13 gave a characteristic magnitude around -20.5 and faint end slope around -2. The faint end slope of -2 was dramatically steeper than lower redshift values of -1.3 to -1.6, indicating an explosion of faint galaxy numbers at early times. 10 times more galaxies existed at absolute magnitude -17 than at -20. This steep slope contradicted expectations that supernova feedback should suppress low-mass galaxy formation more efficiently in the early universe when metallicities were lower and cooling less efficient. The characteristic luminosity of -20.5 closely matched redshift 3 values around -21, showing little evolution between redshift 10 and 3. Standard models predicted characteristic magnitude should be 1 to 2 magnitudes fainter at redshift 10, corresponding to lower stellar masses and younger ages. The observed value meant bright galaxies at redshift 10 were as luminous as those at redshift 3, despite having 1 billion years less time to assemble. The bright end excess, more galaxies, brighter than characteristic luminosity than the Schechter function predicted, was the most striking feature. The exponential cutoff predicted galaxies at absolute magnitude -22 should be half as numerous as galaxies at -20. JWST found the ratio was 0.8 with no significant drop-off. This indicated a much shallower cutoff than exponential, suggesting a broken power law or double Schechter function might fit better. Modifying the luminosity function to a double power law allowed different slopes below and above the characteristic luminosity. Fitting redshift 10 to 13 data gave a faint end slope of -2 and bright end slope of -0.5, indicating continued power law behavior at high luminosities without exponential suppression. The physical interpretation suggested different formation mechanisms for the brightest galaxies compared to standard hierarchical assembly through gradual mergers. Active galactic nucleus contamination provided one explanation. Supermassive black holes accreting gas emitted ultraviolet light that added to stellar emission, making galaxies appear brighter. A galaxy with stellar absolute magnitude -20, hosting an active nucleus, contributing 30% of ultraviolet light, would appear at magnitude -20.6, artificially populating the bright end. If 10 to 30% of bright redshift greater than 10 galaxies contained active nuclei, they could create an apparent bright end excess even if the true stellar luminosity function had normal exponential cutoff. Separating active nuclei from stellar emission required identifying broad emission lines with velocities exceeding 1,000 km per second, or high ionization emission lines, characteristic of hard radiation fields, around black holes. JWST NIRSPEC spectra of 4 bright galaxies at redshift 10 to 12 showed one clear active nucleus with broad hydrogen emission, one possible active nucleus with elevated neon emission ratios, and 2 purely stellar systems. This 25 to 50% active nucleus fraction was higher than 5 to 10% typical at redshift 2 to 3, suggesting black holes were more common or more active at early times. The rest frame optical luminosity function, measuring brightness at 5,000 angstroms, tracing older stellar populations rather than just young stars, provided complementary information. Rest frame optical at redshift 13 corresponded to observed 7 micrometers, accessible to JWST MIRI. The optical to ultraviolet luminosity ratio measured stellar age. Young populations had ratios around 0.5, old populations had ratios around 2 to 3. MIRI detected only the brightest redshift greater than 10 galaxies due to sensitivity limits. For 5 galaxies with ultraviolet absolute magnitudes brighter than -20. 5. MIRI measured optical to ultraviolet ratios of 0.8 plus or minus 0.3 intermediate values, indicating mixed young and old stellar populations. This confirmed these galaxies weren't pure starbursts, but contained significant evolved stellar masses, consistent with ages exceeding 200 million years and validating spectral energy distribution, fitting results showing substantial stellar masses. The next 10 years of cosmic exploration and what they could unveil. The controversy surrounding JWST's discoveries will be settled definitively over the next 5 to 10 years. through systematic spectroscopic confirmation campaigns, deeper imaging revealing fainter galaxies, and multi-wavelength observations with ALMA, Chandra, X-ray Observatory, and next-generation ground-based telescopes. Multiple observational programs are already underway or planned to confirm or refute the most extreme claims. JWST Cycle 3 allocated 800 additional hours for spectroscopic follow-up of high redshift candidates identified in Cycle 1 and 2. The JWST Advanced Deep Extragalactic Survey is obtaining ultra-deep 100-hour integrations on select fields, reaching spectroscopic sensitivity to detect oxygen emission lines from galaxies at absolute magnitudes as faint as -16.3, magnitudes fainter than current limits. These observations will reveal whether the steep, faint end slope continues to fainter magnitudes or flattens, determining the total ionizing photon budget available for reionization. The Cosmos Webb program, covering half a square degree in the cosmos field, represents JWST's largest area survey. This 255-hour program is imaging 0, 54 square degrees to magnitude 27.5 across 4 filters, identifying thousands of galaxy candidates at redshift 6 to 13. The large area minimizes cosmic variance, the statistical uncertainty from surveying limited volumes, providing robust measurements of number densities and luminosity functions. Cosmos Webb will determine whether JWST's initial discoveries represent typical galaxies or rare outliers in overdense regions. Ground-based spectroscopic facilities are obtaining independent confirmations. The Keck Observatory's Mossfire spectrograph can confirm redshifts for galaxies brighter than magnitude 25.5 inches 2 to 4 hour integrations. The Very Large Telescope's excess shooter spectrograph, covering 0.3 to 2.5 micrometers simultaneously, can identify multiple emission lines, confirming redshifts unambiguously. Gemini Observatory's Flamingos 2 and NIRS instruments provide complementary near-infrared spectroscopy. These facilities will spectroscopically confirm or refute hundreds of JWST candidates over the next 3 years. The extremely large telescope, with its 39-meter mirror coming online in 2028, will revolutionize high redshift spectroscopy. Its Harmony integral field spectrograph will obtain spatially resolved spectroscopy for galaxies at redshift greater than 10, measuring rotation curves, metallicity gradients, and dynamical masses with 10 times better sensitivity than JWST. The Giant Magellan Telescope's 25-meter equivalent aperture and 30-meter telescope, if constructed, will provide similar capabilities, enabling detailed characterization of early galaxy properties. ALMA is conducting large programs targeting molecular gas and dust in JWST galaxies. The Rebels program observed 40 galaxies at redshift 6 to 8, with follow-up extending to redshift 10 to 12. The Crystal program is mapping carbon monoxide, ionized carbon, and dust continuum in 28 galaxies at redshift 4 to 7, with extensions to higher redshift. These observations will determine gas masses, gas kinematics, and star formation efficiencies in early galaxies, testing whether gas reservoirs and depletion times match expectations. The Origins Space Telescope, a proposed NASA mission for the 2032, would carry a 5.9-meter cryogenic telescope observing mid- and far-infrared wavelengths from 2.8 to 588 micrometers. This would detect dust emission from redshift greater than 10 galaxies currently invisible to JWST, MIRI, and ALMA, determining dust masses, temperatures, and compositions independently. Origins would map polycyclic aromatic hydrocarbon features and far-infrared fine structure lines, tracing gas, cooling, and metallicity. The Lynx X-ray Observatory, another proposed mission, would carry a 3-meter X-ray telescope 100 times more sensitive than Chandra. Lynx would detect X-ray emission from supermassive black holes in galaxies at redshift 10 to 15, measuring black hole masses and accretion rates independently of optical spectroscopy. This would reveal whether the apparently high black hole to stellar mass ratios at high redshift are real or artifacts of selection effects. The Square Kilometre Array Radio Telescope, under construction in Australia and South Africa, will eventually observe neutral hydrogen 21 cm emission from galaxies at redshift 6 to 15. This would directly map the distribution of neutral hydrogen during reionization, measuring when and where ionized bubbles formed around first galaxies. Combined with JWST galaxy identifications, SKA would connect ionizing sources to ionized regions, constraining escape fractions and reionization topology. Gravitational wave observations provide another probe of primordial black holes. If primordial black holes with masses 10,000 to 100,000 solar masses comprise dark matter, they would occasionally merge, producing gravitational waves detectable by future space-based detectors like LISA, the Laser Interferometer Space Antenna, launching in the 2030 seconds. The merger rate and mass distribution would reveal what fraction of dark matter consists of primordial black holes, testing whether they could serve as seeds for supermassive black holes. Multi-messenger observations combining electromagnetic, gravitational wave, and neutrino astronomy will probe exotic physics in the early universe. If cosmic strings' one-dimensional topological defects from phase transitions existed, they would produce gravitational wave backgrounds detectable by pulsar timing arrays and distinctive lensing signatures in JWST images. If dark matter consisted of particles decaying or annihilating, gamma-ray and neutrino telescopes would detect signals from high redshift structure where dark matter densities were highest. The next decade will determine whether JWST's discoveries represent a crisis requiring revolutionary new physics or an evolutionary step refining our understanding of galaxy formation within the standard cosmological framework. Spectroscopic confirmation campaigns will separate genuine high redshift galaxies from lower redshift interlopers. Deeper observations will reveal whether number densities remain anomalously high at fainter magnitudes. Multi-wavelength observations will constrain stellar masses, ages, and black hole properties independently. By 2035, we'll know definitively whether the Big Bang needs saving or replacing, JWST's findings, and the possibility of a universe we didn't expect. If spectroscopic observations over the next few years confirm that most of JWST's galaxy candidates are genuinely at redshift 10 to 16, with the masses and ages currently measured, the implications cascade through every branch of physics and cosmology. This isn't a minor adjustment to existing theories. It's a complete breakdown of our understanding of how the universe works. The age of the universe would be the first casualty. Multiple independent measurements, cosmic microwave background temperature fluctuations from Planck, radioactive dating of the oldest stars in globular clusters, expansion rate measurements from type Ia supernovae, and Big Bang nucleosynthesis predictions all converge on 13.8 billion years with less than 2% uncertainty. These aren't connected measurements that could share a common systematic error. They're completely independent physical processes measured through entirely different techniques. If galaxies containing 500 million-year-old stars existed just 250 million years after the Big Bang, those stars formed before the Big Bang occurred. There's no wiggle room here. You can't fudge the numbers by 10 or 20% and make it work. The discrepancy is a factor of 2 or more. Either every single one of these independent age measurements is catastrophically wrong in exactly the same direction, by exactly the same amount, which strains credibility, or something much stranger is happening. One possibility: the Big Bang wasn't actually the beginning. The cyclic universe models propose that our universe underwent infinite cycles of expansion and contraction, with each Big Bang actually being a bounce from a previous contracting phase. If structure from a previous cycle somehow survived the bounce and seeded galaxy formation in our current cycle, galaxies could be older than our Big Bang, while the universe as a whole is infinitely old. But these models face severe theoretical challenges. How does information survive a singularity? What physics operates at Planck scale densities? Current cyclic models predict specific signatures in gravitational waves and cosmic microwave background polarization signatures we haven't detected. Another possibility: time itself worked differently in the early universe. If physical processes ran faster when the universe was younger, if 1,000,000 years of stellar evolution at redshift 20 accomplished what would normally take 100 million years, then you could compress stellar evolution, timescales. But this requires fundamental constants of nature to vary with cosmic time or density. The speed of light, gravitational constant, or fine structure constant would need to be different in the early universe. Measurements of atomic spectra in distant quasars constrain such variations to less than 1 part in 100,000 over cosmic history, far too small to explain JWST observations. Dark energy's equation of state would need radical revision. The standard cosmological constant model assumes dark energy density remains constant as the universe expands. If dark energy density was much higher in the early universe, it would accelerate expansion more aggressively, effectively giving galaxies more time to form relative to the cosmic clock. Early dark energy models with density decreasing from high values at redshift 30 to low values at redshift 10 could provide factors of 2 to 3 additional effective time for galaxy formation. But these models must simultaneously explain low redshift observations, dark energy behavior today, and match cosmic microwave background constraints, an extraordinarily tight needle to thread. The dark matter particle would likely need complete replacement. Cold dark matter particles with masses above 1 kilo electron volt moving at non-relativistic speeds produce the observed large-scale structure through hierarchical clustering. Simulations following billions of dark matter particles from cosmic microwave background epoch to today successfully reproduce galaxy distributions, cluster masses, and cosmic web topology we observe, except for these impossibly early, massive galaxies. If dark matter consisted of different particles with different properties, warmer, self-interacting, or clustered on different scales, structure formation would proceed differently. But decades of experimental searches for dark matter particles have found nothing, and alternative dark matter models struggle to match the full range of observations, from dwarf galaxies to galaxy clusters to gravitational lensing. The entire lambda cold dark matter framework might require abandonment. This 6-parameter model has successfully explained virtually every cosmological observation for 30 years. Cosmic microwave background, anisotropies, large-scale structure, type Ia supernova distances, baryon acoustic oscillations, galaxy clustering, weak gravitational lensing, and hundreds of other independent measurements. Finding a replacement framework that explains all these observations while simultaneously allowing massive early galaxies seems nearly impossible. It's like discovering your perfectly functioning car engine actually violates thermodynamics. Something's wrong. But replacing the engine means redesigning physics. Stellar evolution would need dramatic revision. The timescales for stars to burn hydrogen, evolve off the main sequence, produce heavy elements, and explode as supernovae are determined by nuclear physics and quantum mechanics operating under known temperature and density conditions. These processes have been tested in laboratories, observed in nearby stars, and verified in stellar clusters of known ages. If stellar evolution somehow proceeded 5 to 10 times faster in the early universe, the fundamental rates of nuclear fusion reactions would need to be different. That requires changing nuclear cross-sections, binding energies, or reaction pathways, modifications that would affect Big Bang nucleosynthesis predictions for primordial element abundances, potentially invalidating those successful predictions. Galaxy formation efficiency would need to approach 100%. Currently, only about 1 to 3% of gas in molecular clouds successfully forms stars, with the rest blown away by feedback. In the early universe, with more massive stars and more energetic supernovae, efficiency should be lower, not higher. If somehow efficiency was 50 to 100%, with essentially all available gas converting to stars on the shortest possible timescales, it contradicts everything we understand about turbulence, magnetic fields, and radiation pressure in star-forming regions. Such high efficiency might be possible if feedback mechanisms were suppressed, if supernovae somehow didn't expel gas, or if magnetic fields couldn't support clouds against collapse, but we have no physical mechanism that would cause such suppression. Supermassive black hole formation would require entirely new mechanisms. Growing 4.0 million solar mass black holes in 420 million years while respecting the Eddington limit is mathematically impossible, starting from stellar mass seeds. Direct collapse black holes solve the timing problem, but require extremely rare conditions occurring in less than 0.01% of halos. Primordial black holes formed during inflation solve the timing problem, but face severe observational constraints. If JWST black holes are real, we need either a new black hole formation mechanism producing 100,000 solar mass seeds commonly in the early universe, or a new accretion mechanism exceeding Eddington limits by factors of 10 to 100 sustained for hundreds of millions of years, or primordial black holes comprising a larger dark matter fraction than current limits allow. The philosophical implications cut deeper than physics. We've built modern cosmology on the principle that the laws of physics are universal and unchanging. The same nuclear reactions, gravitational physics, and quantum mechanics operating everywhere and everywhen. JWST observations challenge this assumption. If different physics operated in the early universe, are the laws of nature truly fundamental or merely effective descriptions that change with conditions? If physical constants varied with cosmic time or density, what determines their values? These questions move beyond empirical science into metaphysics. The sociological implications for science itself would be profound. Cosmology has achieved extraordinary predictive success, predicting the cosmic microwave background's detailed properties decades before measurement, predicting the acceleration of cosmic expansion before discovery, predicting specific patterns in galaxy clustering confirmed by observations. This track record built confidence that cosmologists understood the universe's history. A fundamental breakdown at redshift 10 to 15 would shatter that confidence. How many other aspects of cosmology are wrong? Can we trust any extrapolation beyond directly observed epochs? The crisis would likely trigger decades of theoretical exploration and observational verification before new consensus emerges. The relief of a normal universe. If the James Webb Telescope is mistaken, the alternative scenario that systematic errors, selection biases, or misinterpretations explain JWST's apparently impossible discoveries would represent a huge relief for physics while teaching valuable lessons about the challenges of studying the early universe. Several plausible systematic errors could individually or collectively resolve the tensions. Photometric redshift contamination remains the leading candidate. Without spectroscopy, redshift estimates rely on colors measured through multiple filters. A galaxy at redshift 2 containing substantial dust could absorb its blue light, creating color patterns mimicking a galaxy at redshift 12. The Lyman alpha break technique assumes the sudden drop in flux at specific wavelengths comes from neutral hydrogen absorption. But dust absorption can fake this signature. Early estimates suggested photometric redshifts had uncertainties around plus or minus 0.5. But for galaxies at extreme redshifts with unusual spectral energy distributions, uncertainties might reach plus or minus 2 or more. Spectroscopic follow-up has already shown significant contamination. Galaxy CEERS 93316. Initially placed at redshift 16.7 based on photometry, turned out to be at redshift 4.9, off by a factor of more than 3 in redshift, corresponding to a factor of 6 in cosmic time. If 50% of photometric candidates above redshift 13 are actually at redshift 4 to 8, the extreme high redshift population shrinks dramatically, potentially consistent with theoretical predictions. The key question: what's the true contamination rate? Is it 20%, 50%, or 80%? Spectroscopic confirmation campaigns over the next 3 years will answer this. JWST has now obtained spectra for about 50 candidates, with photometric redshifts above 10. The confirmation rate so far runs about 70%. Most candidates confirm at high redshift. Some drop to much lower redshift. If this rate holds for the remaining hundreds of candidates, the high redshift population remains large enough to create tensions. But if confirmation rates drop below 30% for the most extreme candidates above redshift 13, the crisis largely evaporates. Stellar population model uncertainties represent another systematic, converting observed colors and spectra into ages, masses, and star formation. Histories relies on models of stellar evolution and stellar atmospheres. These models have been calibrated on nearby stars and stellar clusters in the Milky Way and local group, but early universe conditions differ dramatically. Metallicities 10 to 100 times lower than solar values means stellar atmospheres radiate differently. Initial mass functions might be weighted toward massive stars rather than the standard distribution. Binary star evolution complicates things further. About half of stars form in binary systems that interact and exchange mass, changing their evolution. Updated stellar population models incorporating these effects can shift derived ages and masses by factors of 1.5 to 2. If current age estimates of 200 million years are actually 100 million years, and current mass estimates of 10 billion solar masses are actually 5 billion solar masses, tensions ease considerably, though don't completely disappear. Validating these models requires detailed spectroscopy of extremely metal-poor stars in the Milky Way. Halo stars, formed in conditions similar to redshift 10 galaxies, work that's ongoing but not yet definitive. Active galactic nucleus contamination could explain the brightest, most massive galaxies. If 30 to 50% of ultraviolet light in these systems comes from accretion onto supermassive black holes rather than stars, inferred stellar masses drop by factors of 1.5 to 2. Star formation rates inferred from ultraviolet luminosity would similarly decrease. Lower masses and star formation rates mean longer assembly times and more plausible formation scenarios. Identifying active galactic nucleus contamination requires high signal-to-noise spectroscopy, detecting broad emission lines or unusual ionization states, observations JWST is obtaining for the brightest candidates. Dust attenuation corrections might be systematically wrong. Converting observed ultraviolet luminosity to intrinsic luminosity requires correcting for dust absorption. Standard corrections use extinction curves measured in nearby galaxies, but early universe dust might have different compositions, less graphite, more silicate, different grain size distributions producing different extinction curves. If dust in redshift 10 to 13 galaxies absorbs less ultraviolet light than standard curves predict, dust corrections are overestimated, meaning true star formation rates are lower than calculated. Lower star formation rates, integrated over cosmic time, produce less stellar mass, easing tensions. Size measurements critically affect inferred properties. A galaxy measured with half-light radius 0.5 kiloparsecs, but actually 0.25 kiloparsecs, has 1/4 the area, 4 times higher surface density, and very different implications for star formation and dynamics. JWST's resolution of 0.063 arcseconds corresponds to 360 light-years at redshift 13, barely resolving many candidates. Accurate sizes require careful point spread function modeling and deconvolution. Uncertainties in sizes translate to uncertainties in surface densities, dynamical masses, and specific star formation rates. If sizes are systematically overestimated by factors of 1.5 to 2, many derived properties change favorably. Gravitational lensing magnification offers a reality check. Galaxy clusters magnify background galaxies by factors of 2 to 20 or more, depending on position. Observing the same galaxy lensed into multiple images with different magnifications allows reconstruction of intrinsic properties. JWST has observed several galaxy clusters specifically to find lensed high redshift galaxies. For the few cases with successful lens modeling, intrinsic properties generally align with unlensed measurements, suggesting sizes and masses are approximately correct. But larger samples are needed to definitively rule out systematic biases. Cosmic variance, statistical fluctuations from surveying limited volumes could make early results unrepresentative. JWST's initial observations covered about 2 cubic megaparsecs at redshift 10 to 13. Density fluctuations at these scales, a substantial factor of 2 overdensities or underdensities, are common. If JWST preferentially observed overdense regions due to gravitational lensing cluster fields or accidental targeting of protoclusters, observed number densities could exceed cosmic averages by factors of 2 to 5. The Cosmos Web survey, covering 30 times larger volume, will test whether initial fields were representative or outliers. Even if JWST's observations are perfectly accurate, theoretical models might simply underestimate early galaxy formation efficiency. The simulations predicting sparse, low-mass galaxies at redshift 10 to 13 include approximate prescriptions for star formation, supernova feedback, and chemical enrichment processes occurring on scales of parsecs to hundreds of parsecs, far below simulation resolution of kiloparsecs. These subgrid models are calibrated on lower redshift observations where galaxies are directly observable. Extrapolating to redshift 10 to 13, where conditions differ dramatically, is risky. Perhaps star formation efficiency was higher, feedback was weaker, or gas accretion was faster than models assumed. Tuning these subgrid models to match JWST observations while maintaining agreement with lower redshift observations would represent evolutionary rather than revolutionary progress. It would mean our understanding of galaxy formation was incomplete but not fundamentally broken. The lambda cold dark matter cosmological framework would survive intact. The Big Bang age would remain secure. Stellar evolution and nuclear physics wouldn't need revision. Astronomers would breathe a collective sigh of relief and get back to work refining models. The lesson: extraordinary claims require extraordinary evidence. JWST's initial photometric observations suggested extraordinary claims. Before upending fundamental physics, the community needs extraordinary evidence through systematic spectroscopic confirmation, multi-wavelength verification with ALMA and other facilities, and careful evaluation of all possible systematic errors. This process takes years, not months. The final verdict remains several years away. Beyond cosmic origins, the questions that defy our understanding of time. Beyond the technical questions of galaxy masses and formation timescales lies a deeper puzzle about cosmic origins and the nature of time itself. If some structures truly appear older than the universe, it challenges our understanding not just of astrophysics, but of causality, cosmology, and perhaps even the arrow of time. The concept of the beginning carries immense weight in cosmology and philosophy. The Big Bang theory doesn't just describe how the universe evolved. It posits an absolute beginning, a moment before which nothing existed. No space, no time, no matter, no energy. Not empty space, but the absence of space itself. This concept emerged from Einstein's general relativity in the 1920 seconds, was resisted for decades as philosophically troubling, and finally gained acceptance through overwhelming observational support. But what does beginning even mean? In our everyday experience, events have causes that precede them in time. Your birth was caused by your parents' existence. Their existence was caused by their parents, and so on backward through time. But the Big Bang breaks this chain. It's an uncaused cause, an effect without a prior cause, because prior loses meaning when time itself begins. This troubled scientists and philosophers alike. Fred Hoyle proposed the steady-state model specifically to avoid this conceptual difficulty, imagining an eternal universe without beginning or end. Observational evidence ultimately ruled against steady state, but the philosophical discomfort remained. If JWST galaxies are genuinely older than the universe, several radical possibilities emerge. First, the Big Bang wasn't the beginning but a transition. The ekpyrotic scenario, derived from string theory, proposes that our Big Bang resulted from the collision of two three-dimensional membranes in a higher dimensional space. Before the collision, both branes existed with their own space-time structures. The collision created our observable universe, but didn't create existence itself. In this view, before the Big Bang is meaningful, it refers to the state of the colliding branes prior to impact. Second, time is not fundamental but emergent. Some quantum gravity theories suggest that time emerges from more fundamental quantum information structures at Planck scales. At sufficiently high densities approaching the Big Bang, classical time might break down, replaced by quantum superpositions of different temporal sequences. In this framework, asking what happened before the Big Bang is like asking what's north of the North Pole. The question assumes a coordinate system that doesn't exist in that regime. Structures appearing older than the Big Bang might reflect quantum uncertainty in temporal ordering near the cosmic origin. Third, we're observing structures from a different universe entirely. Eternal inflation theory proposes that inflation, the exponential expansion in the first fraction of a second, is eternal and ongoing, continuously producing pocket universes. Our observable universe is one such pocket where inflation ended and normal expansion began. But other pockets formed earlier in the eternally inflating multiverse. If somehow we're detecting galaxies that formed in an older pocket universe, perhaps through quantum tunneling or wormhole connections, they could appear older than our local Big Bang while being younger than the multiverse as a whole. Fourth, causal structure itself is more complex than we understand. General relativity permits closed time-like curves paths through space-time that loop back to their own past. While these usually require exotic matter with negative energy density, they're not forbidden by the equations. If the early universe contained exotic topological structures like cosmic strings or traversable wormholes, causal loops might be possible. A galaxy that formed at cosmic time t could influence its own formation at earlier time t minus delta through a closed time-like curve, creating apparently a causal evolution. The arrow of time itself might be reversed or undefined in the early universe. The second law of thermodynamics, entropy always increases, defines the direction of time we experience. But this law is statistical, not fundamental. At the Big Bang, the universe started in an incredibly low entropy state, all energy concentrated in a tiny volume. Why? This initial condition problem has puzzled physicists for decades. Some speculate that entropy near the Big Bang might not have been at absolute minimum, and that time's arrow could be different or even reversed in the earliest moments. The cosmological constant problem connects to these deep questions. Quantum field theory predicts vacuum energy density should be 10 to the 120th power, times larger than observed the worst prediction in physics. If vacuum energy was indeed much higher in the early universe and somehow decayed to current values, it would dramatically affect expansion rates and structure formation timescales. The physics of this decay might involve new fields, phase transitions, or quantum effects we don't understand. This rolling cosmological constant could effectively give the early universe more time for structure formation. Anthropic selection introduces another layer of complexity. If the multiverse contains infinite universes with varying physical constants and initial conditions, we necessarily inhabit one where galaxy formation occurred, stars formed, planets developed, and life emerged, because otherwise we wouldn't exist to make observations. Universes where galaxy formation was impossible or occurred differently would be unobserved. This doesn't explain JWST's observations, but contextualizes them. Even if our local universe's properties seem finely tuned or improbable, anthropic selection ensures we find ourselves in a universe compatible with our existence. The simulation hypothesis offers an exotic alternative. If we exist in a computer simulation, the apparent contradictions could reflect computational limitations, programming errors, or intentional oddities added by simulators. Observable universe properties would reflect not fundamental physics, but the simulation's implementation details. While this hypothesis is unfalsifiable and scientifically unsatisfying, it's been seriously discussed by philosophers and physicists. JWST observations of apparently impossible galaxies might be bugs in the cosmic code. These metaphysical speculations venture beyond empirical science into philosophy, but they're not idle speculation. If JWST observations are confirmed and can't be explained within conventional cosmology, we'll be forced to consider radical alternatives. The history of physics shows that revolutionary observations often require revolutionary interpretations. Relativity overturned absolute time and space, quantum mechanics overturned determinism and classical causality. Dark energy overturned the assumption of decelerating expansion. JWST might be forcing another paradigm shift. The verdict: revolution or evolution? After examining the evidence from every angle, the observations, the theoretical predictions, the potential systematic errors, the alternative explanations, and the deeper implications, what's the most likely resolution to JWST's crisis? The answer combines elements of both revolution and evolution, but leans ultimately toward evolution with significant modifications to galaxy formation theory rather than complete overthrow of cosmology. The smart money bets on a combination of factors reducing but not eliminating the tension. Spectroscopic follow-up will likely confirm 50 to 70% of photometric candidates at genuinely high redshifts, while revealing 30 to 50% as lower redshift contaminants. This immediately reduces the number density of extreme galaxies by a factor of 2 to 3. Of the confirmed high redshift galaxies, more careful analysis, incorporating active galactic nucleus contamination, updated stellar population models, and refined size measurements will probably reduce typical stellar masses by another factor of 1.5 to 2. These corrections combined reduce inferred stellar masses by factors of 3 to 6 compared to initial estimates. A galaxy initially estimated at 100 billion solar masses at redshift 13 might actually contain 15 to 30 billion solar masses once properly analysed. That's still massive for the epoch, still 3 to 6 times higher than standard models predict, but no longer impossibly massive. The crisis shifts from existential to severe, but potentially resolvable. Galaxy formation simulations will be updated with revised subgrid models for star formation, feedback, and gas accretion, calibrated specifically to match JWST observations, while maintaining agreement with lower redshift data. These updates will likely involve higher star formation efficiencies at redshift greater than 10, perhaps 5 to 10% instead of 1 to 3%, justified by lower metallicity, reducing cooling inefficiency. Weaker feedback in the early universe, due to rapid gas accretion, replenishing expelled material, might allow sustained star formation despite supernovae. Cold gas streams, funneling material directly to galactic centers, might bypass some feedback mechanisms that operate in galaxy outskirts. The lambda, cold, dark matter cosmological framework will survive essentially intact. The 6 parameters from Planck will remain secure. The universe age of 13.8 billion years will stand. Dark matter will still be cold and collisionless. Dark energy will still be a cosmological constant or very close to it. But the mapping from dark matter halos to galaxy properties, the baryonic physics of star formation and feedback, will require significant revision at high redshift. This represents evolution, not revolution. Supermassive black holes present a harder problem. Even with factor of 2 corrections to black hole masses, growing 2 0-million solar mass black holes in 400 million years requires moderately super-Eddington accretion or more massive seeds than stellar remnants. Direct collapse black holes will become the favoured seed mechanism, with theoretical work focused on understanding what environmental conditions trigger direct collapse and why these conditions might be more common than current simulations predict. Perhaps the first galaxies formed preferentially in mini-halos, with conditions favourable for direct collapse. Perhaps population 3 stars left intermediate mass black hole remnants more commonly than thought. The reionization history will be revised to begin earlier, around redshift 12 to 15, with the ionizing photon budget provided by faint galaxies below JWST's detection limits. The steep faint end luminosity function slope of -2 means enormous numbers of faint galaxies existed, perhaps 10 times more galaxies at absolute magnitude -15 than at -20. These galaxies, while individually faint, collectively produce substantial ionizing photons. Combined with escape fractions around 30% in low metallicity early galaxies. This budget suffices to ionize the universe by redshift 6, consistent with quasar observations. The most lasting impact will be humility. Cosmologists were confident they understood galaxy formation from detailed simulations run on supercomputers following billions of particles through cosmic history. JWST demonstrated that this confidence was premature. The early universe remains poorly understood. Extrapolating from redshift 2, where observations are plentiful, to redshift 12, where observations were previously absent, is treacherous. Nature surprised us, as she often does. The lesson: empirical data always trumps theoretical expectation. This pattern repeats throughout astronomy's history. Before Hubble, the prevailing theory held that the universe was static and eternal. Hubble's observations of galactic redshifts overthrew this, revealing an expanding universe. Before the Cosmic Background Explorer satellite, theorists debated whether the hot Big Bang model was correct. COBE's precise measurement of the cosmic microwave background spectrum settled the debate definitively. Before Hubble's observations of distant supernovae, astronomers assumed cosmic expansion was decelerating. The supernovae revealed acceleration, forcing introduction of dark energy. Each time, observations surprised theorists, forcing revisions to fundamental assumptions. JWST is following this tradition. The observations are real, the galaxies exist, whether at the claimed redshifts or somewhat lower. Their properties are surprising regardless of exact distances. This surprise will drive theoretical progress over the next decade. New simulation techniques with better resolution and more realistic physics will be developed. New stellar population models incorporating binary evolution and rotation will be created. New observations with JWST, ALMA, and next-generation ground-based telescopes will constrain the problem from multiple angles. By 2035, we'll have a comprehensive picture of galaxy formation from the first 100 million years through cosmic noon at redshift 2 to today. We'll understand how the first stars formed, how quickly they enriched their surroundings with metals, how efficiently gas converted to stars under different conditions, and how feedback regulated star formation across cosmic time. We'll know whether supermassive black holes formed from stellar remnants, direct collapse, or primordial black holes. We'll map reionization's progress in detail through 21 centimeter observations. The narrative arc will run from initial surprise through confusion and debate, then gradual convergence toward consensus as observations accumulate and theories adapt. This is how science works, not through revelation or authority, but through careful observation, critical analysis, theoretical innovation, and eventually, hard-won understanding. JWST has given us a gift, a mystery to solve, a puzzle demanding our best efforts, a reminder that the universe still holds surprises. Whatever the final resolution, we're privileged to witness this moment in astronomy's history. Future generations will look back on the 2020 seconds as the decade when humanity first glimpsed the universe's earliest galaxies, confronted unexpected complexity in cosmic dawn, and worked collectively to understand how the first structures formed. The images are spectacular. The science is profound. The journey toward understanding has barely begun. The universe is 13.8 billion years old. The galaxies JWST discovered formed in the first 200 to 400 million years. Their stars shine across 13.4 billion years of space and time to reach our telescopes. In their light, we read messages from the cosmic dawn, messages that challenge, perplex, and ultimately illuminate our understanding of existence itself. Whether these galaxies are impossible or simply improbable, Whether they break the Big Bang or bend our theories, they remind us of a fundamental truth. The universe is under no obligation to make sense to us. Our job is to make sense of the universe. And that work continues.